Hi, students. This lecture is over chapter 11, which is fluid mechanics. Okay, so this is the last chapter of the theory of mechanics. And so all along we've been talking about is, and I started talking about this in a very first lecture, and that is we're developing the theory of mechanics. We're really getting close to being done. The theory of mechanics, let's remind ourselves what that means. It is a study of objects in motion. In all three modes of motion. And that is, remember, translation, rotation, and oscillation. And in all three major states of matter. And you knew this before coming into this class. Three major states of matter: solid, liquid, and gas. Okay, liquids and gases together are referred to as fluids. Okay, so body of water, like what's like water in a swimming pool, or flowing water out of your faucet in your sink, that's a fluid. Air, like the air you breathe, that's a fluid. Oxygen gas, that's a fluid. So both liquids and gases are fluids. So in our study, we have talked about how Newton's laws and how mechanics can successfully describe objects in translation, rotation, and oscillation. We finished oscillation in chapter 10. Now, so far in our study of physics, we have really only studied solid mechanics. That is, objects that are involved are solids. Even if it's a liquid, like a raindrop, we still treated it as a solid. Now we're going to relax that, and we're going to consider the other two states of matter, liquids and gases. And so chapter 11 is fluid mechanics. All right. So that, and then when we get done with fluid mechanics, we get done with chapter 11, that is mechanics. That is the theory of mechanics. We have completed then at this point one theory in this class. We'll have one more theory to complete. That's the theory of thermal physics. All right. Now, fluids. So the study of fluids at rest is called fluid statics. So fluid statics would be like a placid lake or a swimming pool, without anybody swimming in it. Basically just a pool of water or a glass of water, something where the liquid is stationary or the fluid is stationary. Then we have Then we have the study of objects, of fluids, and motion. Is fluid dynamics. So fluid dynamics might be a flowing river, a flowing stream of air, or a flowing, let's say stream of air, for instance. Fluids that are in motion. It could be water flowing out of a faucet. All right, so now in OpenStax actually dedicated, the previous book actually dedicated 2 chapters to fluid dynamics, or fluid mechanics. Chapter 11 was all about fluid statics. Chapter 12 was all about fluid dynamics. In this book, in your book, Cutnell and Johnson, and you're actually going to have 1 chapter devoted to everything. So chapter 11 is going to be the entirety of fluid mechanics. We'll start studying in chapter 11, we'll start studying effectively fluid statics, and toward the end, we'll talk about Bernoulli equation. We'll talk about fluid dynamics, but it's all wrapped up in 1 chapter. It's all chapter 11 in your current textbook. Okay, so let's get going. So you start thinking about, the claim that this got done making, that we can study fluids, or we can use Newton's laws or the mechanics that we've talked about so far in this class to study fluids. Well, you start kind of wondering how do you do that? Let's kind of imagine a popsicle. Let's say I make myself a popsicle. How do you make a popsicle? Well, you have a cylindrical vessel that you fill with water. Maybe you put some Kool-Aid in there to sweeten it, and you put it in the freezer, and eventually you have a solid cylindrical chunk of ice. Now, let's say I instead of consuming that, I decide I'm going to do physics experiments on it. Well, that chunk of ice, I can push it with a pen, or I push it with my finger, and I can move it. I can throw it. I can make it into a projectile. I can roll it. I can do all manner of things that I studied in chapters 1 through 10. But if you didn't freeze that water, it's the same H2O, the same water. Well, if I decided, well, I'm going to put it on a mass meter. The ice, I can put it on a mass meter. I want to weigh it. I stick it on a mass meter. No problem. But if I decide I'm going to put the liquid on a mass meter, all I'm going to do is create a mess. So I can't even weigh it in a normal way, in a normal sense. If I want to go and apply a force to it, well, if I push the ice with my finger, I can just move it. But if I push my finger into the liquid water, my finger is just going to sink into the liquid water. So again, at first glance, you look at that and say, well, how do you apply the physics of chapters 1 through 10 to a fluid, like a liquid water, for instance? How do you apply that? Well, you can apply it, but you have to kind of dress it up a little differently, all right? And so with fluids, and we can do this with solids. Let's say I don't have a mass meter, and I want to figure out the mass of a particular solid. What might I do? Let's say the solid, let's say, for instance, I have a solid, let's say it's in the form of a rectangular cuboid. So I want the mass. But I do not have a mass meter. Or a scale. What do I do? Well, let's say this object is some sort of rectangular cuboid. So I can draw one. Let's say this cuboid has, let's say, a width W, a height H, and a length L. Right? So I say, well, and I happen to know what the cuboid is. Let's say I know the density. Someone tells me it's made out of steel or something. Let's say I know the material. Of which the object is made. All right, so I can look up in a book or maybe my iPhone, and I can figure out what the density of it is. So I can find out the density. Mass density. The mass divided by the volume. Well, why is that important? Well, that's important because I can take the density and I say, well, that's the mass divided by the volume. And I can solve for the mass. I can just cross multiply and say, well, mass is the density times the volume. Well, I can look up the density in a book someplace or maybe on my iPhone. And I can as accurate as hell, I can get calipers or whatever it is I can do. I can measure accurately. I can measure the, let's say the volume of this. What is the volume? Well, length times width times height, right? So I can measure the volume of this object very accurately. And if I know the density and I multiply it by the volume, I get the mass. I don't need the mass meter. I can get the mass by other means. Okay, and so, well, that's true for solids. Might be very well the object is too big. I have to do it this way. But generally speaking, there's an alternate way I can find the mass without even needing a scale. I can multiply the density and the volume. Well, with let's say fluids, you don't have a choice. Well, fluids, that's one way to do it. I mean, you could be clever and say, well, I have this container, and I'll measure the mass of the container without the fluid. I'll put the fluid in, measure the two together, and then subtract. I mean, I could do that too. But in general, let's say for instance, your container happens to be a swimming pool. Well, you can't do that so easily. Well, what might you do? Well, what you could do is you could figure out what the volume of this, let's say it's full of some sort of liquid. You got this liquid in here, and let's say for instance the area of this vessel, say it's cylindrical, its height. Well, what I could do is say, well, I know what the liquid has a certain volume. Maybe it's water. I figure out, I look up what the density of water is. And what I can do at this point is say, well, I know that the density and that the mass is the density times this volume. Or I can say that the mass is the density times, let's say, A times H. The volume is the area of the cross-sectional area is A and the height is H. So again, I can totally, without even needing to worry about mass meter or needing to worry about doing things the old-fashioned way, I can figure out what the mass of the substance is. All right, so I just dress it up differently. I mean, essentially, to do mechanics, what do I need to do? I need to be able to do Newton's second law, writing it out basic sense. Well, I can get the mass this way. I can get the mass by using the concept of a density. What about the force? As I said, I can't just, with the solid, cylindrical ice, I could just push it with my finger, do whatever I want. But now, if I go push my finger in, my finger's just going to sink into that water. So what do I do with the force now? Well, I have to consider a distributed force, and I can do this with solids as well. If I decide, I can use this concept with a solid as well, and I talk about a force distributed over an area now. So what I got to think about is, like, let's say in this particular example of my cylinder, I guess, of water, I may not be able to, let's say, I may not be able to actually put a pin or a linear or concentrated force on there without sinking it. But what I can do instead is I can maybe have a piston. So maybe up on top, I have some sort of a piston. And I can push with a force. But the area is an area A. And so what I can do is I can have a force that's distributed over an entire area. Like in this case, this drawing's not very good, but let's say this case is a piston. So I can distribute a force divided by an area. I can refer to that as a pressure. We call this a pressure. The units are newtons per meter squared, and we refer to that as a Pascal. Named after the great French philosopher and physicist Blaise Pascal. Typically, we will put this in terms of units of PA. So this is named after Blaise Pascal. He was a mathematical prodigy. He was doing advanced mathematics when he was like 7 years old. Pascal didn't live very long. He was always, his entire life, he was very sickly. I think he died around the age of 39. But, given he got an early start because he was a mathematical prodigy, we know about him today. So named after Blaise Pascal, a very important person in science. In fact, there's a programming language named after him. People actually will program in Pascal. So he has concept of the pressure. Now, we call that pascals. In English units, you might have pound per square inch, which we call PSI. You might see, your cars, needs, 36 PSI of air pressure. You might have pounds per feet squared. So again, the force in English units is the pound, and typically you have some sort of English units on the bottom. Usually I see it as inch squared. Sometimes you might have feet squared, but generally speaking, for most applications, it's PSI, pounds per square inch. Okay. So we can capture the force. Again, cross multiplying, I can refer to the force as, say, the pressure times an area. So I can get the force back with pressure. I can get the mass back with density and volume. And so with this said, I can actually capture the units that I need in order to be able to do mechanics. I'm not for a loss. I just have to dress things up a little differently. Okay, let's get started with a few problems to kind of get our feet wet here. I want to look at OpenStax 11.1. All right, so it says gold is sold by the troy ounce. Which is 31.103 grams. What is the volume of 1 troy ounce of pure gold? So gold is sold by the troy ounce, which is 31.103 grams. What is the volume of 1 troy ounce of pure gold? Okay, so let me erase this. Okay, so what do we know? Well, 1 troy ounce of gold, so our mass is going to be 31.103 grams, or divided by 1,000. We have 0.03103 kilograms. Okay. The density. You have to look up one way or another. Your book has a density table, chapter 11. But the density of pure gold, as you look it up or ask your iPhone what it is, you have 19.32 times 10 to the third kilograms per meter cubed. So we want to find the volume. Well, what do you do? Well, density again is the mass divided by the volume. So change partners here. That means the volume is the mass divided by the density. All right. So the mass, we have 0.031103 kilograms. And the density is 19.32 times 10 to the third kilograms per meter cubed. And so in so doing, you find out that the volume is 1.61 times 10 to the negative 6 meters cubed. Or if that doesn't make any sense, what we can do is we can say, well, let's just convert that. We know that there's 100 centimeters in a meter. You got to cube that conversion, of course, because it's cubic. And you could also write down in maybe a little bit better units, 1.61 centimeters cubed. So 1 troy ounce of gold has a volume of 1.61 centimeters cubed. Okay. Let's do 11.4. Open stacks, 11.4. That one says a straightforward method of finding the density of an object is to measure its mass. With the mass meter. And then measure its volume by submerging it in a graduated cylinder. What is the density of a 240 gram rock? that displaces 89.0 centimeters cubed of water. Okay, and this is if you can't measure the volume through direct measurement, and one of the ways to measure the volume is to see how much water it displaces. Essentially, it'll remove that much. The volume of water that is removed is essentially equal to the volume of the object. Essentially, the object is replacing that much water. So the water's got to go someplace. So it basically the overall volume of the fluid becomes increased. That difference in volume is the volume of the object that's been displaced. And effectively, we were meeting face to face. That would actually, our very, very first experiment that we would meet face to face would be real basic experiments of measuring densities, essentially understanding the concept of precision of measurements in the lab. And one of the things, we would measure densities by measuring volumes through this measurement of dimensions. But if you had an odd shaped object, then you'd have to displace water, right? So that's another way of doing it. So again, what are we talking about? Well, we know the mass, we know the volume displaced, so it's a very simple calculation. Find the density. Okay, and so the density of water becomes, or the density of not water, density of this object becomes its mass, or the mass divided by the volume displaced. So the density of object, density of rock. So rho is the mass of the rock that you measure with the mass meter divided by the volume of the water that it displaced, right? And so it simply becomes 240 grams divided by 89.0 centimeters cubed. And it's quite simply 2.70 grams per centimeter cubed. It's probably one of the simplest calculations we do in this class, but it's important. So density, we're just finding, these are again, when you're talking about a new study, you have to start off with your basics. Okay, let's do OpenStax 11.6. That one says a rectangular gasoline tank. Can hold 50.0 kilograms of gasoline when full. All right, what is the depth of the tank? If it is 0.500 meters wide, and 0.7900 meters long. And then B, discuss whether the gas tank has a reasonable volume. Okay, for a passenger car, sorry. That's right. All right, so we're gonna try to make some physical, so get some, see if this is reasonable. All right, so 11.6 open stack. So rectangular gasoline tank can hold 50.0 kilograms of gasoline when full. What is the depth of the tank if it is 0.500 meters wide and 0.900 meters long? B, discuss whether the gas tank has reasonable volume for a passenger car. All right. So looking up, we're gonna need a density. So, you look up an open stacks 11.6. You look up in the book and you find out that the density of petrol is 0.68 times 10 to the third kilograms per meters cubed. Density of petrol or gasoline. Okay. Now, well, what do? Well, you have that the density is mass divided by the volume, and we can solve and say, well, that means that I know the density, I know the mass. I mean, the mass we're told is 50 kilograms, right? So the density is the mass divided by the volume. I can switch partners and say, well, that means that the volume is the mass divided by the density. And the volume, well, I'm being told the area of the gas tank. I don't know the depth. So I can say that the volume is really the area times the depth is equal to the mass divided by the density. And I can solve for the depth. So I can say the depth is equal to the mass divided by rho A. And I'm ready to go. The depth of the gas tank, well, see, the depth would be the 50 kilogram mass, all divided by the density of petrol, 0.68 times 10 to the third kilograms per meters cubed. And the area is what? It's going to be 0.500 meters times 0.900 meters. If I do that, I find that the depth is going to be 0.163 meters. Depth of the gas tank. All right. So that's the answer to part A. That's A. I know the depth now. Now the question is this reasonable? Is this a reasonable volume? Does this make for a reasonable volume for the gasoline tank of a passenger car? All right, so let's remember this number, and let's figure out if this is reasonable. Does this calculation make sense? So, how do we figure it out? Well, the volume is the length times width times depth, right? And so the volume is going to be 0.500 meters times 0.900 meters. I may have those two backwards, but it's okay. Times 0.163 meters. When you work all that out, you get that the volume is going to be 7.34 times 10 to the negative 2 meters cubed. But we don't think about cubic meters in the United States. We think about gallons, right? So a gallon, you look this up, A gallon has 3.785 times 10 to the negative 3 meters cubed. And that gives us a volume of about 19.4 gallons. My car holds about 20 gallons. I have a Chrysler Town and Country, so that's reasonable for a good sized car. 19.4 gallons is a reasonable amount of gasoline to hold. So yes, this is reasonable. For a passenger car. Okay. That's 11.6. That's the calculation of density. Let's do a calculation of pressure. This was going to kind of tell you that pressure can work for solids, as we'll see in this next question. This will be kind of a little bit surprising, I think, to some of you. So 11.11 open stacks. It says, as a woman walks, she is momentarily, her entire weight is momentarily placed on one heel of her high-heeled shoes. Calculate the pressure exerted on the floor by the heel if it has an area of 1.50 centimeters squared and the woman's mass is 55.0 kilograms. Okay, express the pressure in Pascal. It says in the early days of commercial flight, women were not allowed to wear high-heeled shoes because the aircraft floors were too thin to absorb this large pressure. So you'll actually be surprised how much pressure is actually exerted on the floor. It's not, something that maybe people don't really think about, but it's actually very significant. All right. So again, it says, as a woman walks, her entire weight is momentarily placed on one heel of her high-heeled shoes. Calculate the pressure exerted on the floor by the heel if it has an area of 1.50 centimeters squared and a woman's mass is 55.0 kilograms. Express the pressure in Pascal. All right. It's a pretty easy calculation, but again, it's one of those things that, you can kind of see something that might surprise you. So let's erase this. Okay, so let's look at the, let's calculate the air, see the area. Centimeters squared is not going to do us any good. So let's put that into meters squared. So I have 1.50 centimeters squared. I always got to go to SI. So let's see here. 1 meter has 100 centimeters. Quantity squared. We find out the area will be 1.50 times 10 to the negative 4 meters squared. That's the area. And so the force, so we're going to look at the pressure. The pressure is the force over the area. Well, the force is brought out by her weight. So it'll be mg divided by A. So we find out, we know her mass is 55 kilograms. Gravity, 9.80 meters per second squared, gravitational acceleration, divided by A, which we determined to be 1.50 times 10 to the negative 4 meters squared. We find that the pressure is 3.59 times 10 to the 6 pascals, 3.5 million pascals is the area exerted under her high heel. So again, it seems probably to be quite surprising. I mean, basically you apply a force over a smaller and smaller area, you get a greater pressure. That's how a knife works. A knife is such a small, thin area that you apply a force, you create enough pressure to cut something. So again, applying a force over a very smaller area increases the pressure. Okay. Next topic is anybody who's ever gone swimming realizes that the lower you get in the water, the greater the depth, you start feeling a greater and greater pressure on you. The pressure becomes much greater. And so there's a variation of pressure with depth. I mean, essentially, we feel a pressure of 1 atmosphere just on the surface of the Earth. So on the surface of the Earth, we feel an air pressure of 1 atmosphere. We call it atmosphere is one of the units of pressure. So I guess I'll just call it atmosphere. Hopefully you've seen this in your chemistry class. Its abbreviation is ATM. And that is equal to 1.013 times 10 to the 5th pascals. So we talked about, newtons per meter squared. Well, and this pressure is caused by the weight of a column of air over a 1 meter squared area where that column extends from the surface of the Earth to the top of the atmosphere. So that entire weight of air, just air, over a meter squared area, all the way from the ground all the way to the top of the sky, is exerts a pressure, an atmospheric pressure everywhere of what we call 1 atmosphere, 1 atm, which is also 1.013 times 10 to the 5th Pascal. So you have air exerting pressure on you all the time, everywhere. And the air pressure is not that great because air is pretty thin. If you go to some place like Venus, Venus has an atmosphere of sulfur dioxide. So the air pressure at the surface of Venus is so great that it would crush anything. There's only been one man-made spacecraft that has ever seen the surface of Venus. And that was some Russian probe that was launched, I don't know, 30 years ago or so. And that Russian spacecraft lasted a few seconds, and it just got crushed by the great pressure at the surface of Venus, because Venus's density is so much greater. So again, the pressure at the surface is the weight of the entire atmosphere over that 1 meter squared area. Okay, so you're always feeling that. Well, let's say you get into a swimming pool. Okay, and let's say in the swimming pool you have the entire weight of water above you as well, plus the weight of the atmosphere. So you say you go to the bottom of a pool first, so I have a big pool, and let's say there's water in it. Okay, and we have water, and the water's going to have a weight, right? The weight is going to be mass times gravity, like weight would be anywhere else, right? And let's say that this water has a height h, and let's say there's an area a. All right, so you have water, and so we're wondering what the water is. Let me do this a little bit better. Say we have the water, we know there's an area A down here at the bottom. We're going to say the area, we'll say this is a cylinder, so the area and top and bottom are the same. You're saying, well, okay, what's the pressure at the bottom? I want to find the pressure at the bottom. So I want the pressure at the bottom of pool. What's that again? Well, that's pressure is the force divided by the area, just like the previous example of the woman's shoe, or woman's heel. Force over the area. In this case, the force is being caused by the weight of the water, the mass of water. So again, same calculation as the previous problem, mg over A. But again, I can't, unlike the woman who could stand on a scale and find her mass, I can't find the mass of this water very easily. I have to involve the density concept, right? So instead, I'm going to say, well, I know that the mass is really the density times the volume times g divided by A. Oh, and the volume is the area times the height. So that means that the pressure is the density times the area times the height times g divided by A, and the A's cancel. That means that the pressure varies by density as by height is rho gh. There's a linear relationship between pressure and depth, and the slope of that relationship is rho times g. Rho is assumed is constant, and g is constant. So those are two constants. The only thing that varies is depth. So pressure varies directly proportional to depth. P equals rho g, so rho gh, the linear relationship. The greater the depth, the greater the pressure, and it's a linear relationship, right? So linear relationship. The variation of pressure with depth. That's all there is to that derivation. Let's do a couple problems. Okay. Get our feet wet with this. Looking at 11.14 OpenStack. All right, that says, what depth of mercury? Creates a pressure of 1.0 atmosphere. All right, so, well, pressure, 1.00 atmosphere. Again, that's one of the units of pressure, atmosphere. But we want to do our calculations in SI, right? And so we want to convert that automatically to SI. We know that there's 1.013 times 10 to the 5th pascals, and this can be looked up, per 1 atmosphere. So really the pressure that we want is 1.013 times 10 to the 5th pascals. That's the pressure of 1 atmosphere. That is the SI unit for pressure. The density of mercury, you can look this up. The density of mercury is 13.6 times 10 to the 5th, or sorry, 10 to the 3rd kilograms per meter cubed. Density of mercury. So remember, chemists, mercury is Hg. All right. So what do? Well, I know that the pressure is linearly related to the depth, rho g h. Let's solve for h. H is the pressure divided by rho g, or 1.013 times 10 to the 5th pascals divided by 13.6 times 10 to the 3rd kilograms per meter cubed. That's density of mercury. And then divided by gravity, gravitational acceleration, 9.80 meters per second squared. I find that H is equal to 0.760 meters. Or, you might remember this, 760 millimeters of mercury. So if you look up in a book, maybe your chemistry book, or maybe your physics book, you want to find atmospheric pressure. Well, they'll give it to you as one atmosphere, 1.013 times 10 to the 5th pascals, or it creates a column of height 760 millimeters of mercury. We'll talk a little bit more about that in a moment. Millimeters of mercury is another way of measuring pressure. So that's another one that they'll give you in the book, is 760 millimeters of mercury. So we can remember this for a later problem, all right? So the 1 atmospheric pressure, 760 millimeters of mercury, okay? Okay, let's look at another problem, 11.15 of OpenStax. That one says the greatest ocean depths on the Earth. Are found in the Marianas Trench. Near the Philippines. Calculate the pressure. Due to the ocean. At the bottom of the trench. Given its depth is 11.0 kilometers. And assuming the density of seawater is constant all the way down. So, OpenStax 11.15. The greatest ocean depths on the Earth are found in the Marianas Trench near the Philippines. Calculate the pressure due to the ocean at the bottom of the trench, given its depth is 11.0 kilometers, and assuming the density of seawater is constant all the way down. Okay, so this is going to be kind of an incredible calculation. I mean, well, it's an easy calculation, but it's going to be incredible, the answer is. All right, so here we go. So what do we have here? Well, we're told the depth is 11 kilometers, 11,000 meters. That's almost unthinkable. And the density of seawater, we look it up, density of seawater is 1,025 or 1.025 times 10 to the third kilograms per meters cubed. So a little more dense because of the salt than fresh water. And what do we do? Well, P, pressure, is rho g h. Simple as that. The pressure is 1.025 times 10 to the third kilograms per meter cubed times 9.80 meters per second squared times 11,000 meters. Pressure is 1.10 times 10 to the 8th pascals. Let's get this into something that we can kind of relate to. So 1 atmosphere has 1.013 times 10 to the 5th pascals. So the pressure at the bottom of the Marianas Trench is 1.09 times 10 to the third atmospheres. It's about 1,000 times the pressure felt at the surface of the Earth. We have only recently been able to get submersibles down to have scientists look at the bottom of the Marianas Trench. For the longest time, you know, we would have submarines go down there and they would start dangerously leaking and have to submerge. So we couldn't even, you know, there's more people that have actually walked on the surface of the moon than have walked near or been near the bottom of the ocean. And what scientists actually thought that near the bottom of the ocean, you would actually get to a point where you'd have almost no life. And yet, to their great surprise, there's an entire new universe of life crawling at the bottom of the Marianas Trench. So life is so diverse and so adaptable that even at the incredible pressures of 1,000 times the pressure felt at the surface of the Earth, you still have a diversity of life. Now the life moves very, very slowly. All these animals down there move very, very slowly to conserve their energy. So it's almost like a slow motion form of life. But one of the other things the scientists happen to see down there at the bottom of the Marianas Trench, besides life they didn't expect, is they happen to see at the very lowest part of the Marianas Trench a plastic bottle of empty plastic water bottle. So even at the greatest depths of the ocean, even that region is not protected or immune to human littering. So anyway, keep that in mind. So even at the bottom of the ocean, even though they discovered something really beautiful like this diverse life, and they also discovered that we humans are even polluting that. So anyway, interesting. So that's the calculation of pressure and how pressure varies with depth. Now we typically, and a lot of you guys are are going to the medical field, and typically we use pressure to like for instance, when you go to the doctor's office, the first thing the doctor does is puts a blood pressure cuff on you and tests your blood pressure, right? And the question is, well, how does that work? How you're putting a blood pressure cuff on my bicep, and yet somehow it's supposed to measure the pressure in my blood. How does that work? So, well, the principle that allows us to understand this is a very, very interesting, very beautiful principle in physics. It's called Pascal's principle. Yes, that Pascal we just got done talking about here with the pressure unit. Blaise Pascal is the first person to put forth what's called Pascal's principle. All right, so Pascal's principle is extremely useful, and we use it not only in medical world, we also use it in hydraulics. All right, so it's very, very important. So so our next topic is Pascal's principle. Okay. So Pascal's principle in its basic form is stated in the following way: a change in pressure applied to an enclosed fluid is transmitted undiminished. Very important word. To all portions of the fluid. And to the walls of the container. All right, so Pascal's principle, and we'll kind of get ourselves a nice example of this. So essentially, the important words here. So change in pressure. I'm going to apply some sort of pressure to this fluid, and that's going to be important. We're going to understand here that pressures actually add. So every source of pressure is going to add to the total pressure. So for some reason, like let's say your heart applies. It's basically a pump. It applies additional pressure to the fluid in your body. That extra pressure will actually be transmitted. And again, it's an enclosed fluid. It means that it's a fluid that's not going to go anywhere. I mean, I can push on the fluid let's say in a river, and the fluid will just flow away. And it's not going to, but in an enclosed fluid can't go anywhere. That means that the enclosed fluid is going to have an increased pressure. So enclosed fluid is very important in this. So this change in pressure applied to an enclosed fluid is transmitted undiminished means that pressure is not, there's no losses anywhere. That pressure is perfectly transmitted. Undiminished, not a single loss. It is perfectly transmitted everywhere to all portions of the fluid and to the walls of the container. Everywhere. It is transmitted undiminished everywhere throughout the entire fluidic system. All right. So what's a good application of this? Well, let's talk about hydraulics first. All right. And so let's imagine here for a moment that I have, let's say, a chamber. I'm going to try to draw this thing as low as I can. Get to watch the artist work here. Not beautiful over here. All right, here. Okay, so this is basically going to be full of fluid. Okay, now on one side I have a piston, and on the other side I want to make the other piston at the exact same height. Do the best I can to make them the same height, but this one's gonna have a bigger area. All right. Okay, so what we have here is this is full of fluid, all right? So we're going to imagine that this is all full of fluid. Some hydraulic fluid, as we call it. All right, it's fluid everywhere. So here's fluid, there's a connecting line. This is oftentimes called the hydraulic line. So it's a little connecting line in between, and a bigger chamber. Now, the idea here is that I'm going to apply these. Each of these are pistons. So these are pistons. So pistons are at the same height. So at the same gravitational potential energy. So you can't say, well, one's different than the other because they're at a different height. No, same gravitational potential energy. All right. Now, I'm going to apply a force F1. So I will, or one way or the other, there will be an applied force F1. This is applied force. So in my system, and then we're going to say that this area of this piston is an area A1. This piston has an area A2. Area A1, area A2. And A2 is greater than A1. All right, so A2 is greater than A1. A2 is a bigger area. So I have an external force F1, which is causing an external pressure, P1. P1 is F1 over A1. Okay, so I'm creating this external pressure someplace on external to the fluid. Pascal's principle states that this additional pressure, this pressure's add, this additional pressure is going to be felt everywhere throughout the entire fluid and everywhere on the walls of the fluid, everywhere. So additional pressure will be felt everywhere and undiminished, including right here. That pressure is also going to be felt everywhere, including at the second cylinder. Now, that second cylinder, any pressure there, well, what do we know there? Well, that pressure would have to be given by F2 over A2. All right, and so what we see here is we can basically employ Pascal's principle. And we can basically see that they're equal, right? So essentially, if that's the case, then I have what's called a hydraulic equation. That F1 over A1 is equal to F2 over A2. Very simple. We call this a hydraulic equation. So what's this mean? Well, let's say I have a small area and I apply a certain force. It's going to give a pressure. That pressure is going to cause, so let's say I have an area, let's say it's call it size A. Well, if that same pressure, if I have an area, let's say 5 times the size, it's going to create a pressure it's going to create a force that's 5 times as well. So I can get something, I can essentially get a mechanical advantage, a great mechanical advantage. And that because of the size of the area of the cylinder, now typically I didn't create these terms, but the cylinder where the applied pressure is occurring, that's typically called the master cylinder. And the cylinder that responds to this applied pressure is called the slave. I didn't create these terms, but those are the terms. So the master cylinder is typically smaller. The slave cylinder is larger. You get a larger force. So essentially, I might have a small cylinder on the side, maybe in a garage, where I can lift the 2,000 kilogram car by just applying a small force. All right, and the other advantage of this is that this doesn't have to be a straight line, hydraulic line. This could be this could be routed. This could be in all kinds of different, it could be in, maybe in 3 different, branches. Be tortuous. I mean, it doesn't really matter as long as it's connected and enclosed. So I could snake it around something, and as long as this particular chamber and the other chamber is connected, it doesn't matter. So you have this situation where you get this basically a mechanical advantage, and it's even better than that, in that you can make this hydraulic line as tortuous, as curvy as you possibly want, and you also get no losses. Okay, so let's do a couple of equations here, or sorry, a couple of examples or a couple of problems. So again, this is called the hydraulic equation. Let's apply it. So let's see, OpenStax 11.25. Says, what force must be exerted on the master cylinder of a hydraulic lift to support the weight of a 2,000 kilogram car. A large car resting on the slave cylinder. Okay, let's see here. The master cylinder is a 2.00 centimeter diameter. Okay, and the slave has a 24.0 centimeter diameter. Okay, so question, OpenStax 11.25. What force must be exerted on a master cylinder of a hydraulic lift to support the weight of a 2,000 kilogram car, a large car, resting on the slave cylinder? The master cylinder has a 2.00 centimeter diameter, and the slave has a 24.0 centimeter diameter. All right, so again, I'm going to erase this and let's do the problem. So the hydraulic equation is pretty simple. Okay, so F1 is what we're looking for. That's the force on master cylinder. Okay, A1, we'll say the area of the master cylinder. A1 is pi d1 squared over 4. So pi r squared if we know the radius, and pi d1's pi d squared over 4 if it's the diameter. So again, I gotta put these in SI units. So 0.022 centimeters, 0 meters, quantity squared divided by 4. We find out the area of the master is 3.14 times 10 to the negative 4 meters squared. Area of master. All right, and then F2 is the weight of the car. That's mg. That's the weight that's sitting on the slave cylinder. That's going to be 2,000 kilograms times 9.80 meters per second squared. F2 is going to be 19,600 newtons. Okay. A2, okay, and this is basically the that's the force that's to be lifted by the slave. And A2 is pi d2 squared over 4, or pi times, it was the slave cylinder was 24 centimeters, so 0.24 meters. 20 squared divided by 4. And we see that the area of the slave is 4.52 times 10 to the negative 2 meters squared. Area of slave. Okay, I'm ready to apply the equation. I'm going to erase this though, so let's remember what these numbers are. And here we go. So I don't have enough room to actually do the equation, so I calculate all the stuff I needed. We want F1. So the hydraulic equation is simply F1 over A1 equals F2 over A2. Hydraulic equation. We want F1, so just got to multiply both sides by A1. So F1 is A1 over A2 times F2. So A1, we figured out was 3.14 times 10 to the negative 4 meters squared. A2 is 4.52 times 10 to the negative 2 meters squared. That's a unitless number. Multiplied by 19,600 newtons. That's the weight of the car. We find out that we can lift 19,600 newton car with only a force of 136 newtons. So all you have to do is apply 136 newtons to the master cylinder, and the slave cylinder lifts a 2,000 kilogram car, or a car that has a weight of 19,600 newtons. That's an incredible mechanical advantage. That's a hydraulic system. This is brought out because of Pascal's principle. All right, let's look at 11.27 of OpenStax. All right, this says a certain hydraulic system is designed to exert a force (100 times as large as the one put into it). A, what must be the ratio of the area of the slave? So what must be the ratio of the area of the slave cylinder to the area of the master cylinder? That's A. B, what must be the ratio of their diameters? C, by what factor is the distance through which the output force moves? By what factor is the distance through which the output force moves reduced relative to the distance through which the input force moves. If I can fit all this. Okay, says Open Stacks 11.27. A certain hydraulic system is designed to exert a force 100 times as large as the one put into it. A, what must be the ratio of the area of the slave cylinder to the area of the master cylinder? B, what must be the ratio of their diameters? C, by what factor is the distance through which the output force moves reduced relative to the distance through which the input force moves? Okay, so again, remind yourselves of the hydraulic system I drew on the board a little bit ago. All right, let's do these. So, okay. So part A, well, let's kind of define our variables. So we have F sub S and A sub S. That would be a force in the area of the slave. And F sub M and A sub M, the force and area of the master. Okay, and of course, you know, Pascal's principle, a hydraulic equation. Oh, that's right. The hydraulic equation is that F sub M over A sub M is F sub S over A sub S. Hydraulic equation. All right, and so we know that F sub S, you know, the force that is on the slave should be 100 times that you put into it at the master. So it should be 100 F sub M. That means I can then write that F sub M over A sub M is 100 F sub M, just doing a quick substitution, over A sub S. And my F sub M's can cancel out. And I can rearrange and find out that A sub S over A sub M has to be 100. So the area of the slave cylinder divided by the over the area of the master cylinder should be 100, should be a factor of 100. The areas. What does that mean for diameter? Okay, so for diameter, well, let's start off with the last result we just got. That was part A. So part B, for diameters, well, I just got done saying that the area of the slave over the area of the master must be 100. Well, area of the slave, I would say that's pi d sub s squared over 4. Area of the master, pi d sub m squared over 4. The pi's and the 4's cancel out. So what I get is I get d sub s squared over d sub m squared is 100, or take the square root of both sides, I get that d sub s over d sub m is 10. Finally, taking the square root of both sides. So the diameter of the slave over the diameter of the master should be a factor of 10. Okay. Now, part C may seem a little bit weird. Part C, We can think of that if there's a force pushing a piston, it's going to do some work, right? So force F sub m will push the master cylinder a displacement we'll say X sub m. And it's going to push down the master cylinder by some displacement X sub m. Likewise, force F sub s will push the slave cylinder a displacement X sub s. All right. So F sub m does work. F sub m, X sub m. Force times displacement, remember? And F sub s does work. Force times displacement. F sub s, X sub s. And neglecting friction, we're going to say there's no friction here by the conservation of mechanical energy. These two works must be equal. So F sub m, X sub m is equal to F sub s, X sub s. The two works must be equal. All right. So again, as I said, force F sub m will push the master cylinder a displacement X sub m. It's going to push it down. Likewise, the force F sub s will push the slave cylinder a displacement X sub s. F sub m then does work F sub m, X sub m. F sub s does work F sub s, X sub s. Take off friction, we get the conservation of energy tells us that F sub m, X sub m equals F sub s, X sub s. All right, so let's see what that tells us. That argument. So again, I know that F sub m, X sub m is F sub s, X sub s. And I also know that F sub s, remember the slave is going to have 100 times the force on the master. So I can put that in there and say, okay, well, instead of F sub m, I'll say, I'm sorry, F sub s, I'll substitute. So I have F sub m, X sub m is 100 F sub m, right? Direct substitution, times X sub s. The F sub m's cancel. And so I find out that X sub s over F sub m, or X sub m, is 1 over 100. So the slave moves 100th the distance of the master. Okay. All right, so next thing I want to talk about is, given that pressure is so important in fluidic systems, we want to talk about measurement of pressure. And so we have the what's called the gauge pressure, the absolute pressure, and the absolute pressure. So the gauge pressure and the absolute pressure. So we have two different major ways of computing computing pressure. So for instance, let's say you have a totally flat tire. You put your tire gauge in and it reads zero, basically reads zero PSI or 0 pascals, whatever it may be. And you say, well, how is that possible? And I know that pressure is always, there's atmospheric pressure, so why would the tire gauge read zero? Well, the tire gauge reads what is called gauge pressure. So gauge pressure is pressure that, so we have gauge pressure, means basically corrected via an offset. So gauge pressure is the pressure relative to atmospheric pressure. Okay, so gauge pressure is positive. For pressures above atmospheric pressure. And negative for pressures below atmospheric pressure. Of course, atmospheric pressure itself would be zero, like when you measure the totally flat tire. So that's gauge pressure. Gauge pressure is generally the pressures that you will read. And you get your blood pressure taken, for instance, it's gauge pressure. You know, we don't care that we know that the blood pressure is measuring the pressure of the heart during each cyclic heartbeat. But we know that at either side of the heart, there's atmospheric pressure, 1 atmosphere. We don't care about that. It doesn't do anything because it is applying pressure everywhere the same. So we just subtract off that offset. What we really want is the pressure of the actual heart. The pressure of the heart is actually employing or imposing on the body. Now we have in some cases you want to include the atmospheric pressure. If that's the case, then you apply calculate what's called absolute pressure. Absolute pressure is simply, so we have the concept of absolute pressure. And that's simply adding in the atmospheric pressure. So pressure absolute, ABS, will be the gauge pressure, I'll put a little G for gauge, plus the atmospheric pressure. Yeah, then the atmospheric pressure for situations where you want to know the absolute pressure. And the minimum pressure, the minimum absolute pressure is 0. You don't have a negative absolute pressure. Okay. So now the situation, in which we end up measuring pressures typically is, and I kind of alluded to this earlier. We talked about the height of a column of mercury. well, atmospheric pressure is equivalent to 760 millimeters of mercury. You hear that all the time. Well, oftentimes pressure is not, you know, the height that's pushed up by the height that the pressure pushes up in a column of a fluid is typically a lot easier to measure. So let's take a look. For instance, I'm gonna kind of give you a little drawing here. Well, let me actually, you know what? Let me actually give you. Let me project a picture from the textbook. That's even better. Better than trying to figure out my drawings. So I'm going to share my screen here and bring up the textbook. Okay, so we see some pictures of what is called a U-tube manometer. Now, this is not the U-tube where you see my videos. This is a U, like the shape of the letter U, and a tube, like a tube that contains fluid. All right, so the very left one, and you notice that there's a little measuring, there's a little, like a little ruler. Now, the left U-tube manometer is open on both sides of the atmosphere. So I'm looking at the leftmost one here. And you notice that the atmospheric pressure is going to push down equally on both sides. So you'll notice that the level of fluid on each side of the tube is equal. All right? And so, because there's atmospheric pressure pressing equally on both sides of the tube. Now, on the middle picture, what you have looks like a little balloon. And the balloon is on the right side of the tube. And what happens is, well, initially, before you attach that balloon on the right-hand side, you actually initially had the levels being the same, just like in the leftmost picture. Now what's happening is the balloon is employing an additional pressure. So there's the additional pressure, rho GH. So there's an additional pressure that's being applied by the balloon on the right-hand side of the tube. That additional pressure is pushing down the left-hand side of the fluid or pushing up the right fluid. You'll notice that the difference of the two levels of fluid is now going to be equivalent to rho GH. Essentially, that difference in pressure you can measure as a height of fluid. So the fluid height is higher by this amount, because of rho GH. It's being pushed up by this height. This additional height is given this additional height because of the pressure variation with depth. You can actually measure that height and have that be an indication of pressure. So whatever this liquid is, the height of that fluid the height of that fluid that you measure is equivalent to the pressure, the additional pressure, and that's the gauge pressure that's being applied by this balloon. If you want the absolute pressure, you just add P atmospheres. That's a second equation. So you see this equation here is the right-hand side has an additional gauge pressure, rho GH. Rho is the density of the fluid, the working fluid. G is, of course, gravity, and H is this height that you're measuring, rho GH. You want that's the gauge pressure. The gauge pressure is greater than atmospheric pressure. That's why the tube, or the side of the tube that's actually on the side of the balloon is higher. So it's being pushed down. And so what that's indicating is that height is indicating that the pressure, the gauge pressure caused by this balloon is greater than the atmospheric pressure by this amount, rho GH. You want the absolute pressure, you just add the atmospheric pressure. So again, the absolute pressure, the atmospheric pressure plus rho GH. Now on the far right side, you have a vacuum-packed peanut jar. Now again, the vacuum-packed peanut jar is going to have very, very low pressure. In fact, it is below the atmospheric pressure. So you'll notice that the atmospheric pressure now, that particular side of the U-tube manometer is pushing down further. So the right-hand side of the tube is higher by an amount H. Why? Because while the gauge pressure there, well, the pressure is actually below atmospheric pressure. So it actually would be negative gauge, negative rho GH this time. Because that tells you that the pressure inside the peanut jar is below atmospheric pressure. You want the absolute pressure? You have the atmospheric pressure. So again, gauge pressure in this case is negative rho GH because the pressure inside the peanut jar is below that of the atmosphere. And the absolute pressure, you take the atmospheric pressure, and then this time it's minus rho GH. Okay, and so we see the difference between we have positive, we have zero gauge pressure here in the case of the U-tube manometer being open both sides to the atmosphere. Where we have the balloon, we have this balloon device. Well, this is actually higher gauge, higher positive gauge pressure. That means the pressure is higher than atmospheric pressure by what? Rho GH. And when you have the tube attached to the vacuum packed peanut jar, you see that the pressure is actually lower. It's negative gauge. That means it's below atmospheric pressure by an amount rho GH. Okay, so let's put this kind of on the board here to see what we're talking about again. So I'm going to stop. I'm going to bring this picture down. Okay, so again, what I showed you is that what's nice is that I don't have to measure pascals. What I can measure is the height of a column of fluid. It's a heck of a lot easier to measure the height of a fluid than it is a pressure. All right, and so we can actually, so what I just got done showing you again is called a U-tube, not the YouTube what we watch on the computer, but U, capital U, tube manometer. This additional gauge pressure, as I said, it can be positive or negative, is given by rho GH. You know that there is a linear variation of pressure with depth. Basically, there's an equivalent height of a column of a liquid given by this pressure. So instead, you can actually, instead of measuring the pressure in pascals, you can simply say, well, this height of a column of fluid is the pressure, gauge pressure, divided by rho G. So pressure can be measured by the height of a column of fluid. Typically mercury. Mercury is very useful in the medical world. We use it for thermometers. We also use it for manometers. I have a column of mercury, or a column of fluid. Will be general. So typically mercury. Mercury is the only liquid, the only metal that's a liquid at room temperature. All right, so it turns out that in most devices that you actually will use, even if the device looks like it's digital, deep inside of it is a manometer. And that manometer is what you're actually measuring. And so we typically, so for instance, let's say for instance you are doing blood pressure, all right? And so for instance, you have a blood pressure cuff, and then what you're seeing is, well, what are you actually seeing? Well, a mercury manometer is inside, of a blood pressure device. So we'll kind of describe this here for people in the medical industry. So what's the doctor do? Well, doctor is going to put a inflatable cuff around your arm. So doctor wraps an inflatable cuff around your bicep usually. Okay, and then what happens? Well, the doctor uses a bulb. So by squeezing a bulb, you see this, or sometimes it's a machine now. The person making the measurement exerts pressure. So there's pressure on, and which is transmitted undiminished because of Pascal's principle. So transmitted undiminished to both the main artery of the arm and the manometer. Because there's a manometer in this little device. All right. Now, let's kind of continue here. I'll keep that down. So we have the extra pressure. Okay, so I'm gonna erase this. All right, continuing. When the applied pressure exceeds blood pressure, okay, when the applied pressure exceeds blood pressure, the blood flow below the cuff is cut off. Okay, at that time, the person making a measurement then slowly lowers the applied pressure. Okay, slowly measures the applied pressure and listens for blood flow to resume. So usually they'll have a little stethoscope on. All right, and then so blood pressure pulsates okay, because the pumping action, remember the heart's a pump, of the heart reaches a maximum. So the blood pressure pulses with the pumping action of the heart reaches a maximum. Okay, called systolic pressure. And a minimum called diastolic pressure with each heartbeat. All right, so again, after the maximum pressure is applied and the blood flow is cut off, so the applied pressure exceeds blood pressure, the blood flow is cut off. Blood flow below the cuff is cut off. The person making the measurement then slowly lowers the applied pressure and listens for the blood flow to resume. Blood pressure pulsates because the pumping action, basically heart's a pump of the heart reaches a maximum called systolic pressure and a minimum called diastolic pressure during each heartbeat. Okay? And so that is what is being recorded when you get your blood pressure measurements. And so again, to say systolic pressure is the maximum blood pressure diastolic pressure is the minimum blood pressure during each heartbeat. Right? So a healthy person usually reads has a reading of, now again, this is where these numbers come in. They'll usually say, 120/80. Or they might write it as 120/80. And the question is, what on earth does that mean? Well, that means that inside of this blood pressure device is a manometer. And what they really are saying is the systolic is reading 120 millimeters of mercury. That means it's pushing a level of mercury, a column of mercury up 120 millimeters. And at the minimum heartbeat, the diastolic, that one's pushing the mercury up by 80 millimeters. Again, this is just another way of measuring pressure. We're not measuring pascals. Instead, we're measuring a height of a column of fluid. In this particular case, mercury. Okay? And so, generally speaking, to kind of give you an idea, the systolic pressure the doctor's looking for is the number on the systolic pressure okay, that usually measures the maximum output of the heart. And the diastolic pressure, what that measures is the elasticity of the arteries during each heartbeat. So that's what these two numbers measure. And if things are good, 120/80 is roughly what you should be getting. All right. So again, you see pressure all the time, but you wonder, in our regular jargon, you go 120/80. What does that mean? Well, again, it's a height of a column of mercury. You're not measuring in PSI like you would, let's say, tire pressure or pascals. You're measuring it in terms of the height of a column of fluid, and the most popular one to use in most industries, including the medical industry, is mercury. Mercury is very useful. We use it for thermometers. We also use it for pressure devices like manometers. All right. So let me do a couple of problems. I'm going to do OpenStax 11.29. That says find the gauge and absolute pressure. In the balloon, and peanut jar, showing in OpenStax figure 11.16. That's the one I showed you. And you can look that up. You downloaded a book, I hope. Assuming that the manometer connected to the balloon uses water, and that's the fluid and manometer there. Whereas the manometer connected to the jar contains mercury. Okay, expressed in units of centimeters of water for the balloon. And millimeters of mercury for the jar. Oops, millimeters of mercury. Doing a space here. For the jar. All right, we're gonna take H in the picture. So take H, that's the height of the fluid, to equal 0.0500 meters. All right, for each. All right, so find the gauge and absolute pressures in the balloon and peanut jar shown in OpenStax figure 11.16. One I showed you, assuming that the manometer connected to the balloon uses water, whereas the manometer connected to the jar contains mercury, expressed in units of centimeters of water for the balloon and millimeters of mercury for the jar. Take H to equal 0.0500 meters. So in both cases, that's the height of the column of the liquid, 0.05 meters, all right? Whatever the liquid is made, whatever it is, that's what you see in the picture, right? So, the gauge pressure is easy, okay? I'll show you how easy it is. For part A, what do we want? Well, we have water, right? So part A, we're looking at the balloon. And manometer contains water. Okay, well, let's see. We're told that H is 0.0500 meters, right? Well, that's water, right? So we want gauge pressure in centimeters of water, right? The 0.0500. That's so gauge pressure is 5.0 centimeters of water. That's the answer. Simple as that. All I have to do, remember, pressure is in terms of heights of a column of fluid. I'm giving it in SI unit of meters. Now you want centimeters, right? Well, centimeters should just be multiplied by 100. 5.0 centimeters of water, done. That's your gauge pressure. Now the absolute pressure requires a little bit of work. Okay, so absolute pressure, well, I have to deal with water now, right? And so for absolute pressure, I have to take the gauge pressure. I need to add the atmospheric pressure. Atmospheric pressure. So that means that, well, that's the atmospheric pressure, and I got to deal with water. So what do we know again? Oh, yes, that's atmospheric pressure. That whatever the pressure, there's going to be an equivalent height, right? Equivalent column of water in this case. So rho g, and again, what rho? Rho water, right? Got to be specific here. The density of water. We're using water. GH. Rho GH. Remember, it's density. Pressure is direct proportional to depth or height. In this case, height of a column. So I want the height of this. So height is going to be basically the pressure divided by rho g. So it's the pressure, the atmospheric pressure, divided by rho water times gravity. Well, atmospheric pressure in SI is 1.013 times 10 to the 5th pascals. Again, something you can look up. Density of water, that's conveniently 1,000 kilograms per meters cubed. And gravity in SI, 9.80 meters per second squared. What I find when I do that, it's going to be 10.34 meters of water. I want centimeters. I'll multiply by 100. So H is going to be 1,034 centimeters of water. That is the contribution from atmospheric. The contribution from gauge is 5. But I want the total absolute pressure. And remember, the gauge pressure is positive in the case of the balloon. So again, this is going to be what? It's going to be pressure gauge plus rho GH. Or pressure gauge plus atmospheric pressure. So the gauge pressure is positive. Let's see, let's write this down here. Atmospheric pressure plus gauge. Kind of right the way the book has. So again, positive because the gauge pressure is positive. All right, so that's going to be simply 1,034 plus 5, which equals 1,039 centimeters of water. So my balloon device would read a gauge pressure of 5 centimeters of water. And I had to figure out, well, what is the corresponding height of a column of water for the atmospheric pressure? If I had water in a manometer, how much would the atmospheric pressure, what would be the height of a column of water for that atmospheric pressure? Well, it would correspond to a height of what? 10.34 meters, or I want this in centimeters, right? Multiplied by 100, 1,034 centimeters of water. So the absolute pressure is the atmospheric pressure plus the gauge pressure. Gauge pressure is positive, so I can add the two in this case. So 1,034 plus 5 is 1,039 centimeters of water. All right. What about the peanut jar? So the peanut jar, well, again, as you'll see, the getting the gauge pressure will be easy. So again, what was I told? Well, the height of the peanut jar, we're told that height is, again, it was what? 0.0500 meters. Now we're going to say that, okay, now the manometer is not full of water, it is now full of mercury. And I want millimeters of mercury. So how do I get this into millimeters? Well, I multiply by 1,000. So the gauge pressure will be 50 millimeters of mercury. Let's be careful though. Okay, I multiply by, I want to get into millimeters, I had to multiply by 1,000, it gets 50, right? However, be careful. The pressure inside of the peanut jar, the vacuum packed peanut jar, is lower than atmospheric pressure. That means it's not 50, but it's particularly negative 50. Negative 50 is the gauge pressure for the mercury, for the peanut jar. All right, so again, simple as that. Now I'm going to be a little lazy, and I'm going to utilize the work we did in the previous problem. Remember, recall, and we did this in a previous problem. We can go earlier on in here. I don't want to do the calculation again. The atmospheric pressure, remember, for millimeters of mercury, what was it again? 760. Okay, you can look this up in a book. You can write atmospheric pressure, millimeters of mercury. It'll read as 760. And in fact, we actually did the calculation in an earlier problem. So again, I just don't want to repeat the same calculation I did. So there you go. We did that calculation. It's the exact same calculation we just got done doing with water, except you use 13.6 times 10 to the third kilograms meters cubed for mercury, right? And so now, what's the absolute pressure now? Again, absolute pressure is going to be the atmospheric pressure plus the gauge pressure. This time the gauge pressure is negative. So the absolute pressure is the atmospheric pressure that's on 760 millimeters of mercury minus 50 millimeters. So the absolute pressure for the peanut jar setup is 710 millimeters of mercury. All right, and so again, reading the height of a column is real easy. It's a lot easier to measure a distance than it is a pressure. So doing, because of this linear relationship between pressure and height of a fluid, we use height of a fluid just as much or even more so than we use the Pascals, the actual newtons per meter squared formulation. And so we can see that, and then getting to the atmospheric pressure, we can see that's a fairly easy job as well. Okay. I'm going to do OpenStax 11.30 now. Okay, OpenStax 11.30 says, convert normal blood pressure readings of 120 over 80 millimeters of mercury to newtons per meter squared. Okay, using the relationship for pressure due to the weight of a fluid. And All right, I'm not gonna do part B. Part B is just a little discussion thing. So, all right, so I'm just gonna do part A. So how do you do this? Well, you just basically say the P equals rho GH. Simple as this. And so P equals rho GH. So we'll pick the top reading, the 120 millimeters of mercury. So we'll say P systolic, S for systolic, will be, again, mercury is 13.6 times 10 to the third kilograms per meter cubed, 9 times 9.80 meters per second squared, times 120 millimeters is 0.120 meters. Pressure systolic becomes 1.60 times 10 to the fourth Pascal. Pressure diastolic will then be 13.6 times 10 to the third kilograms per meter cubed. G is 9.80 meters per second squared. H now is 0.080 meters. And you do this, you find that the P is supposed to be a letter D here. Pressure diastolic, or P sub D, will then be the corresponding Newton or Pascal reading for this will be 1.07 times 10 to the fourth Pascal. So those are the 120 millimeters mercury and the 80 millimeters mercury reading in Pascal formulation. Okay. Next topic. Next topic is what is called Archimedes' principle. We're still in the study of fluid statics. We haven't started fluid dynamics yet. So Archimedes' principle. Okay, so most, as Carl Sagan once said, I think he said about 90% of all physicists are either employed by universities or the government. I happen to be a physicist who's employed by both. So the government is oftentimes wanting a physicist to work out some calculation for them. And if we go back to Archimedes, Archimedes was a scientist, philosopher in ancient Greece. And of course, ancient Greece, one of the things they wanted to do is they wanted to make good ships. They wanted to make ships, and they wanted to understand the concept of floating. So they asked Archimedes. They asked him to try to solve that problem. So Archimedes was working on this problem, trying to understand it. And then one day he's taking, as the story goes, he's taking a bath, and he's sitting in a bath, and then this concept of flotation came to him, and he got so excited that he jumped out of the bathtub and started running down the street naked, yelling "Eureka, Eureka," which means "I found it, I found it." So the famous story is, you see people, he yelled "Eureka, Eureka." He was so excited, he forgot that he didn't have clothes on. And so he was running down the street, and so he was very excited about this. And this really became the principle of flotation. This allowed the ancient Greeks to make a ship as large as they wanted to, because they were able to understand it. So to understand Archimedes' principle, we have to understand, basically, if you go swimming, you realize there appears to be a force that's pushing you up. You're not just sinking in the water, but you're feeling a force that's pushing aboard, or any kind of a body feels that what's called the buoyant force. All right. So we know that pressure increases with depth. Okay, we've been talking about this for a while now. We've been talking about this where we can actually use a column of a height of a column of a fluid. And so if we take a look, for instance, let's kind of imagine that I have some sort of an object that's located that's submerged in a liquid. We'll just say water, for instance. So I have a situation, I have a tub. And then this tub, we'll say, we like cylinders here, I guess. We'll just say we have some sort of an object that is actually submerged. Let's kind of imagine for a moment that this object that is submerged, and we wonder, well, we know that there's going to be a weight of water above this object, so it's going to feel a weight from the water that's above the object. So we imagine that weight will push down on the object by some amount F1. And we can say that F1 is P1A. There's some sort of a pressure, and the weight of the water above this object is going to. So we'll imagine that that this whole object is full of liquid, right? So this whole thing is full of liquid. All right. So F1 is P1A, right? And we imagine that this is going to be at some sort of a height H1 above the top or from the top. We'll say this is H1, the depth, H1. On the bottom, and we'll imagine this cylinder has an area A. Okay, so the area A on each side of the cylinder. On the bottom, there's a depth of H2 from the top. And there will also be a felt force F2. All right, and F2 will be P2A. And of course, what is the pressure? It's rho GH, right? So in this case, it'd be rho GH1 times A. And in this case, the pressure times the area, well, it would be rho GH2 times A, right? So we can expect that there will be a force that's felt. And so we would expect an overall upward force to be felt. We call this the buoyant force. The buoyant force would be the difference of basically F2 minus F1. We expect F2 to be greater than F1. The pressure down, because of rho GH, the pressure is greater down here. So we expect F2 to be greater than F1. So F2 is greater than F1. So F sub B points upward. Right? The buoyant force points upward. All right, so we see this concept of a buoyant force, and so we say, well, we imagine this buoyant force. We can say that, well, we know that, for instance, that we'll find out that if the buoyant force, if the buoyant force is greater than the object's weight, then the object floats. If the buoyant force is less than the object's weight, then the object sinks. I don't know if you guys are too young to remember David Letterman, You know, he had a, you know, for many, many years, he had this, you know, he had a, I think it was the, I think it's a Late Show, if I recall. The Late Show and the Tonight Show. I think he had a Late Show. No, he had a Tonight Show. I don't remember which, but anyway, one of the jokes he used to have on there, he used to have, will it sink or will it float? And so, you know, again, you know, I always, when I talk about this, I'm always kind of reminded of Letterman's little skit, you know, and will it sink or will it float? And essentially, it all depends on the buoyant force. Now, one of the things to kind of keep in mind here is what happens if you take this object out of the water. Let's say, for instance, now that, okay, we have this object in there, and let's say we take it out, all right? So let me kind of draw another picture to the side and see what happens. Right now, the object is in the tub, it's in the water. Well, let's say what happens now is that I pull the object out. So I'm going to take the object out of the water. Well, if I have, before the object is in the water, you know, what I really have here is that the object is actually taking the place of a volume of water that would otherwise be there. So we imagine for a moment that if I didn't have the object there, there would actually be a volume of water that would actually be there instead. And so instead, we'd have a volume of water that really is now being occupied by this object. So we would have, you know, this would be, you know, H1, and this depth, the bottom, would again be H2. So when I put the object in the place, what I'm actually doing, this is what Archimedes understood, is I'm actually moving or displacing an equivalent volume of water. All right, and so Archimedes' principle, so if you kind of look at this for a moment, what did I say earlier? Well, I said that, you know, the F1, so the buoyant force was what? We can derive this, right? The buoyant force was rho g h, or it's F2 minus F1, which is rho g h2a minus rho g h1a, right? And I can think of this as the buoyant force. I can pull out the rho g. I can basically, I can pull out rho g and a. They're all constant. And I have H2 minus H1 left over. H2 minus H1 is the height of this cylinder, this object that's in there, right? And so what I see here is that the buoyant force becomes rho g. Well, what is it? The height of that cylinder times its area is the volume of that object. Now, if I'm displacing, if I were to ask the question, well, this is the density of water. So if I were to ask, what is the weight of water? And what would it be? Well, let's rearrange this. Put rho and v next to each other, right? What's rho times v? Mass, right? So the buoyant force is actually equal to the mass of the water times gravity, or the weight of the water, or the weight of the fluid. We'll be more general, right? FL for the fluid. Whatever the fluid is. I mean, in this case, I've been saying water, but I'll put FL for the fluid. That's the weight of the fluid. So I've been doing calculations based upon essentially rho, the variation of pressure with depth. But if you do this carefully and you realize, well, the buoyant force is the difference of these two forces, you factor out rho g a, and what's left is the difference of h2 minus h1. Well, h2 minus h1 is the height of the cylinder times a, that is the volume of that cylinder. And well, let's take that volume, put it right over next to rho. Rho times v is what? That's the weight of the water that was displaced, or the mass of water was displaced. Mass of the fluid displaced times g is the weight of the fluid. So Archimedes' principle is the following. This is what Archimedes understood for the very first time. This is how we can make giant, aircraft carriers that float somehow, right? Archimedes' principle says is the buoyant force on an object equals the weight of the fluid it displaces. That is an extremely important principle. How we can make ships. So in equation form, the buoyant force is the weight of the fluid that it displaces. Simple as that. Now we can talk about flotation now. Now that we understand this principle, we can now derive how we can understand if something floats or it sinks. Okay, so let's talk about density as it applies to Archimedes' principle. So we can actually understand this by knowing the density of the object. So let's imagine, for instance, so let's just say I have density and Archimedes' principle. That's my little topic now. So let's just say, for instance, that I see some sort of an object and I see that it's floating. And I basically will say, well, the fraction of that object submerged. The fraction submerged. Well, what would that just be from geometry? Well, that would be the volume of the object that is submerged divided by the volume of the whole object. Okay, no physics there. I'm just witnessing an object. It's floating. Some fraction of it is submerged. Well, it would make sense that it would be the volume of the object that is submerged divided by the volume of the object, right? But I know from Archimedes' principle that the volume of the object that's submerged happens to be the volume of the fluid that it displaces. So I can say, well, that's equal to the volume of the fluid that it displaces by the volume of the object, right? And this is by Archimedes' principle. Okay, and so and I look at it and say, well, the volume of the fluid divided by the volume of the object. Well, let's put this in terms of density. That would be the volume of the fluid. Well, I know the density is mass divided by volume. Well, I can basically write that this would be the mass of the fluid divided by the density of the fluid. And that's the numerator. So I can say instead, I can write that the mass of the fluid divided by the density of the fluid on top. On the bottom, well, I have the mass of whatever the object is made out of by the density of whatever the object is made out of. Okay? Well, if the object floats, Well, we know about that the mass, again, the mass of the fluid, okay, is the same as the mass. I'm sorry, the mass of the object. We're using Archimedes' principle. Is the same as the mass of the fluid displaced. All right, and so the masses cancel. So the masses cancel. Great. So that means that masses are out of there. So I can really say that the volume of the fluid over the volume of the object is going to equal the density of the object divided by the density of the fluid. All right, and so what I just got done saying then all together is that's the fraction submerged. Okay. Putting it all together, the fraction submerged is equal to the density of the object over the density of the fluid. So I can actually determine what fraction is submerged in that case. And again, if you hit 1, then you sink. But you can figure out, what the fraction of an object is that'll submerge based upon these densities. And so how do you make a big aircraft carrier? Well, all you just do is you take a tremendous amount of weight, but you distribute over a very, very big volume. And so hence, as long as the density of the object, the aircraft carrier, is less than the density of water, then the aircraft carrier floats. That's how you get a tremendously heavy object to float. You just make it big enough, such that you make the density small enough. Now, it's typically useful to find a ratio we define a ratio of the density of an object to a fluid, usually water. All right, so when we do that, this is known as the specific gravity. Okay, specific gravity is typically equal to, so the specific gravity is equal to the density of whatever it is, object or fluid you're trying to measure, divided by the density of water. Okay, that's your specific gravity. And that's usually the density of water at 4.00 degrees Celsius, usually. Specific gravity is a unitless number. Why? Because it's density over density. Okay, so unitless number, specific gravity. All right. Now, if specific gravity is less than 1, the object floats in water. If specific gravity is greater than 1, the object sinks in water. All right, so basically knowing the density compared with that of water, you know that the specific you know that whether the object is going to sink or it's going to float. Okay, and again, you know, to remind ourselves here, specific gravity is unitless. It's a ratio of density over density. So there are no units. All right. So let's do some problems. OpenStax 11.36. What fraction of ice is submerged when it floats in fresh water? Given that the density of water at 0 degrees Celsius is very close to 1,000 kilograms per meters cubed. It's liquid water. So actually, that's one thing I don't like about the way this one thing I don't like about OpenStax. When they say water, they assume they assume it's liquid water. I mean, ice is liquid, is solid water, right? So I always kind of put in liquid water at 0 degrees Celsius is close to 1,000 kilograms per meter cubed. All right. So, you know, you guys seen some of these motivation pictures. They always tell you that, you know, that the iceberg is only, the iceberg that you see is only 10% of the actual iceberg. And I've seen these motivation pictures. You see the iceberg, it looks big, but below in the water is 90% of the iceberg. Most of it's, you know, below the water. Well, we're actually going to prove that here. And so we look at density of ice. Okay, so let's erase this, give us some space. So we, you know, typically the motivation pictures or you know, we'll say that the you only see 10% of the iceberg, right? So well, we'll prove that. So the density of ice is going to be, you look it up, it's 0.917 times 10 to the third kilograms per meter cubed. So we want the fraction of the ice submerged. So fraction submerged will be the density of ice over the density of the fluid, liquid water. So fraction submerged will be 0.917 times 10 to the third kilograms per meter cubed divided by 1,000 kilograms per meter cubed. We find out that the fraction submerged is simply 0.917. So it's about 90% is submerged, as we would expect, and about 10% is not. I mean, it's more like about 8% than actually you see. But again, you know, rough numbers. I mean, that motivational picture is more or less correct. 91.7% of the iceberg is submerged. What you see is a little bit more than 8%. And even then, the iceberg looks huge. Okay, next. Open stacks. 11.38. That says find the density of a fluid. Fluid in which a hydrometer having a density of 0.750 grams per milliliter floats with 92.0% of its volume submerged. You know, a hydrometer is a device that measures density. So we would actually use one in the lab. It measures density typically of an unknown fluid. And so usually you see some sort of a ball inside the fluid that you can measure. You can measure the so you have, they call it, it says having the hydrometer itself floats, but what it really says is that you measure the fraction submerged, and then you essentially can compare that with water, the density of water, and figure out the density of this fluid. Right. So the hydrometer is a device that does this. And if actually we're meeting face to face, we would play around with the hydrometer in the lab. All right, so that's what this means. All right, so it means that the hydrometer itself has an object that weighs 0.750 grams per milliliter, and it's going to have 92% of its volume submerged in this unknown fluid. So what is this density of this unknown fluid? That's what we're looking for. That's what a hydrometer does. All right, so let's erase this and do the calculation. So what do we want to use? Well, we're going to say the fraction submerged. is the density of the object over the density of the fluid. Okay, so we know the fraction submerged. %, 0.92. 0, we'll say. All right. Density of the object, well, that's the hydrometer. We know what that is. We know the density of that. That's 0.750 grams per milliliter. So we want the density of the fluid. Simply, you can just change partners here. You can say that the density of the fluid you'll put that up there, put the fraction submerged on the bottom, so you have the density of the object divided by the density of fraction submerged. Well, that would be 0.750 grams per milliliter divided by 0.920. We will find out from this device that the density of the unknown fluid would be 0.815 grams per milliliter. Utilizing this hydrometer. Okay, next problem. I'm going to do open stacks, 11.41. All right, that one says is, okay, this one has to be a little bit more careful. You know, there's going to be some new terminology that we may not have seen before. A rock. With a mass of 540 grams. Is in air, that's its true mass, is found to have an apparent mass. Of 342 grams. When submerged in water. Okay, A. What mass of water is displaced? All right, B. What is the volume of the rock? C. What is the average density? And is this consistent with the value for granite? All right, so 11.41. A rock with a mass of 540 grams in air is found to have an apparent mass of 342 grams. I got to describe what that is when submerged in water. A, what mass of water is displaced? B, what is the volume of the rock? C, what is the average density? And is this consistent for the value for granite? So again, you'd have to look up you have to figure out what the density of the rock is and figure out if that is if that agrees with granite. Okay. Okay. So a lot of little nuances with this problem. And so first of all, we know the mass of the rock. The mass of the rock is 0.540 kilograms, 540 grams. But we really want to do this in terms of SI. 0.540 kilograms is the mass of the rock, first and foremost. All right. Now, we want to figure out what this means, this concept of an apparent mass. What does that mean? So you basically employ Newton's second law. Now, so you have, what do you have here? You have a rock floating, right? So the rock is going to have some sort of a weight mg. Remember, it's floating, so it's going to have some sort of a buoyant force pushing it up. But the rock is going to sink. So it's going to sink at some ma. All right, so if you look at Newton's second law in the y direction will be the buoyant force up minus the weight down is equal to this negative ma, since we know the rock is going to sink. Now, it turns out that this ma on the right-hand side is what we call the apparent weight. The rock is sinking. You know, you have free fall in air. While in this liquid, in water, its free fall is going to be given by this negative ma. So what physicists typically like to do is they take a force and dress it up to look like a weight. So they'll take this ma, this inertial force on the right hand side of Newton's second law, and they'll dress it up to look something like a weight. They'll say, well, let's dress it up to look like an m prime g. I'll make it look like a weight. So my m prime is the apparent mass. So that apparent mass is what you're given in the problem. The apparent mass is if I took this right-hand side Newton's second law and I dressed it up to look like a weight, m prime g. All right. So we're given that m prime in this particular case is 0.342 kilograms. So we're given there. M prime is 0.342 kilograms. All right, so that's my apparent weight. All right, so let's look at how I can figure this out. All right, so now this apparent weight, that's what we're given. So now let's kind of look at how I would do that. So here's my apparent mass. So this would be apparent weight. So let's kind of look at Newton's second law again. All right, and so we know this. We're going to say, okay, well, what we have here is buoyant force minus mg is negative m prime g. And dress it up looking like an apparent weight. All right, and so buoyant force in this particular case, I'm going to put the m on the mg on the other side. So it's going to be mg minus m prime g. Or I can factor out g. So the buoyant force, I can factor out g, and I have m minus m prime times g. So if I know the true mass and I know the apparent mass, then I can actually get the buoyant force. All right, and so in so doing, I can say that the buoyant force is 0.540 kilograms minus 0.342 kilograms times 9.80 meters per second squared. So knowing this information, I can now compute the buoyant force. The buoyant force I find to be 1.94 newtons. Okay, so that's the first thing I want to calculate is the buoyant force. I can get that from the true mass and the apparent mass. All right, now what I want to do is, and again, that's not really what I'm after. I'm after the mass of the water displaced, right? So I need the buoyant force. Now that I know the buoyant force, I will now employ Archimedes' principle. Okay, so now that I know the buoyant force, I can now employ Archimedes' principle and figure out the mass of the water displaced, right? What does Archimedes' principle say? Archimedes' principle. I guess there's an apostrophe there. Archimedes says that the buoyant force is equal to the weight of the water displaced. Okay, that's what Archimedes' principle says. So the buoyant force is the mass of the water displaced times G. If I want the mass of the water displaced, then I take the buoyant force and I divide by G. So that's 1.94 newtons, which I calculated just a few moments ago, divided by 9.80 meters per second squared. I find that the mass of the water that was displaced, is what I'm being asked for part A of this problem, is 0.198 kilograms. So I know the true mass of the rock, I know the apparent mass of the rock. Now I know the mass of the water that is displaced when I put the rock in the water. That's the mass of water displaced, okay? 0.198 kilograms. Okay, 2 more sections of the problem, and we're done with this problem. So now part B, that's part A. Now for part B, what's part B ask me? It says, so part A wants the mass of the water displaced. Part B says, what's the volume of the rock? All right, so how do I figure that out? Well, I go back to that fraction submerged calculation. Now, let's remember these values here. Mass of water displaced, that's important, 0.198 kilograms, all right? Let's remember that. Now, I want to find the volume of the rock. Well, I know that I would start by saying, well, the fraction submerged is what? It is the volume of the fluid divided by the volume of the object. So again, the volume of the water displaced divided by the volume of the object. And that makes sense, you know, because I know the volume that's submerged would be the volume of the fluid, of the displaced fluid, right? But if the rock is entirely submerged, then fraction submerged is 1. Then what that means is that the volume of the object is the same as the volume of the fluid displaced. All right. And so, well, we know that the mass of the water, we just calculated that above, right? Mass of the water, what's that going to be? Well, that's the density of water times the volume of the water. And so we can figure out the volume of the water because what? We know the mass of the water already, and we know the density of water. So the volume of the water is, what was it, 0.198? Is that what it was? 0.198 kilograms. Divided by the density of water, which is 1,000 kilograms per meter cubed. All right. And so if we know that, then we can go straight up and say, okay, well, I'm going to erase some of this now. So if I know that, then I can find the volume of the water displaced. So the volume of the water displaced, doing this calculation, will give me 1.98 times 10 to the negative 4 meters cubed. But given it's entirely submerged, the volume of the water displaced is the volume of the object, which is the rock. So right off the bat, since volume of the object displaced equals the volume of the fluid, the volume of the rock is also 1.98 times 10 to the negative 4 meters cubed. I know that. That's part B. I now know the volume of the rock. And the last part is I want the density of the rock. Well, guess what? I got the mass of the rock, I have the volume of the rock. The density of the rock is a lickety-split calculation. All right, and so we can now do that. So part C is the density of the rock. Density of the rock, whatever it's made out of, is the mass of the rock divided by the volume of the rock. So the mass of the rock is what? We were told in the beginning of this problem, 0.540 kilograms. And the volume of the rock, 1.98 times 10 to the negative 4 meters cubed. The density of the rock, we then find is 2.73 times 10 to the third kilograms per meter cubed. That's the answer for part. That's the answer, and we want to compare that. Well, just so look, if you look it up, that happens to be the density of granite. So likely, whatever this rock is made out of, it's probably granite. All right, next one to do OpenStax problem 11.45. All right, this problem says A, calculate the buoyant force on a 2.00 liter helium balloon. Given the mass of the rubber in the balloon, well, part B, given that the mass of the rubber in the balloon is 1.50 grams. What is the net vertical force? On the balloon. If it is let go. Okay, and then you can neglect the volume of the rubber. Okay, so A, calculate, so 11.45, OpenStax. Calculate the buoyant force on a 2.00 liter helium balloon. B, given that the mass of the rubber in the balloon is 1.50 grams, what is the net vertical force on the balloon if it is let go? You can neglect the volume of the rubber. Okay, so how do we do this? So we start off with a formula: fraction submerged is equal to the volume of the fluid over the volume of the object. Okay, now the fluid is the air in this case. So the fluid is the surrounding air. Okay, and so the mass of the helium in the balloon, and the object's the mass of the helium in the balloon. The object is the helium in the balloon. Okay, so that's what we're talking about. Now, since the balloon is entirely submerged in the air, of course, then the fraction submerged equals 1. So if that's 1, then we can write then that the volume of the fluid is the volume of the object. Or we can write down the volume of the air is the volume of the object, or the volume of the helium. Right? So the volume of the air is equal to the volume of the helium. That's what we can say. All right. So let's and we can say that that's equal to V, common volume. Okay, so that's what we have so far. The volume of the air equals the volume of the helium just equals a common volume V. All right. Now, we can look up in our table, we can look up the density of air is. The density of air we can take as 1.29 kilograms per meter cubed. We can also look up the density of helium. The density of helium is 0.18 kilograms per meter cubed. Look those up. So we can really say then that the mass of the air will be the density of air times the volume of air, which we know is the common volume V. Okay, using that mass as density times volume. We can also say the mass of the helium is the density of helium, again, times the common volume V. All right. Now, by Archimedes' principle, we would say that the buoyant force is equal to what? The weight of the fluid displaced. The buoyant force, the weight of the fluid displaced. That's what Archimedes' principle tells us. All right. And so what we then get is, remember these numbers, the buoyant force equals the weight of the fluid displaced. Well, that means that the buoyant force is the weight of the air. That's what we call the fluid. All right, weight of the air. Well, what would be the weight of the air? Well, we know what the volume V is, right? So that common volume V, we were told that is 2.0 liters. That's the volume of the balloon. So let's figure out that volume now. So 2.0 liters. That was in the given. Now, if you look this up, 1 liter happens to equal 1 decimeter cubed. Kind of a funny little conversion. So a liter is equal to a decimeter cubed. And of course, a decimeter is 0.1 meters in a decimeter. Okay, so we have decimeters cancel. And of course, we have to cube that. All right, and so when we do that calculation, we find out this common volume is actually equal to 2.0 times 10 to the negative 3 meters cubed. All right, and so we want the mass of the air. Well, the mass of the air, we want the weight of the air, right? Well, the mass of the air is going to be the density of air times the volume. Or the density of air, I told you earlier what that was. That's 1.29 kilograms per meter cubed times the volume of air, 2.0. Times 10 to the negative 3 meters cubed. I find out that the mass of the air, okay, when I calculate that, I find the mass of the air to be 2.58 times 10 to the negative 3 kilograms. That's the mass of the air. All right, so I want the weight of the air. We have the mass of the air. Now we want the weight of the air, because that's what the buoyant force is. So buoyant force is weight of the air. Well, weight of the air is mass of the air times gravity. So the buoyant force will be the 2.58 times 10 to the negative 3 kilograms. That I just got done calculating, times 9.80 meters per second squared. All right. When I do this by Archimedes' principle, I find out that the buoyant force on the helium balloon will be 2.53, because buoyant force is equal to the weight of the air displaced. You multiply these two together, you get 2.53 times 10 to the negative 3 newtons, or sorry, 10 to the negative 2 newtons. Sorry. That's the buoyant force. Okay, so that's the buoyant force from the calculation based upon Archimedes' principle. Now, the second part asks, so, okay, well, part B says, given the mass of the rubber in the balloon is 1.50 kilograms, what is the net vertical force on the balloon if it is let go? All right, so in that case, we want the net force. All right, so let's kind of put in our parking lot what our buoyant force is. So I'll kind of write this up here in the parking lot. The buoyant force, we'll just kind of remember what that is. We're going to start part B. Buoyant force, remember, is 2.53 times 10 to the negative 2 newtons. All right, now want the net force. We have the buoyant force, and now we have the total weight. So if we look at this balloon, draw a free body diagram. The buoyant force is going to push up. Down will be what? We have the weight of the rubber, or the total weight, I guess, if you will. And the total, and then essentially, if we want the net force is going to be the buoyant force minus the total weight. Okay, that's the net force. That's what we want in this problem. All right, so the net force on the system will be the buoyant force. Okay, and then minus what? Well, it's the mass of the rubber. And what's the other one? Well, of course, the mass of the helium itself in the balloon. Multiplied by G. I have to account for the rubber that makes up the balloon and the helium. Okay, so net force is the buoyant force. Okay, and then what? Well, we have minus, again, the mass of rubber. I'm given that. And then plus in the parentheses, well, how do you get the mass of gas? Well, it's rho helium times the volume. And that's that common volume. We multiply by G. Okay, so we're now ready to put in numbers. For net force is the buoyant force. Well, that's up there. I just calculated that in part A. So again, this is part B. 2.53 times 10 to the negative 2 newtons minus. All right. We have the mass of the rubber. We're given this 1.50 times 10 to the negative 3 kilograms. All right. And then what? Plus, I'm going to continue over here now. Plus, we have density of helium. We looked that up to be 0.18 kilograms per meters cubed. Okay, density of helium. And then multiplied by the volume of the helium, 2.0 times 10 to the negative 3 meters cubed. And the bracket, and we find out when we do all that, so net force is going to equal, oh, I'm sorry, that's all going to be multiplied by 9.8 meters second squared. We find the net force, when we do all that calculation, will be 7.07 times 10 to the negative 3 newtons. Okay, so net force is just going to be the buoyant force minus the total weight. So net force, and that's what we have here. So it's the buoyant force minus what's the weight? M times G. You have mass of the rubber plus mass of the helium, all multiplied by gravity. So net force, the buoyant force minus what? The mass of the rubber. Well, that was given to us. Helium is the rho helium times that common volume V. That parentheses all multiplied by G. So net force is at 2.53 to the negative 2 newtons that we calculated in part A, minus, I put brackets, 1.50 and 10 negative 3 kilograms, and then plus 0.80 kilograms per meters cubed times the volume, and then all that multiplied by G, get 7.07 times 10 negative 3 newtons. All right, next problem. Let's see here. This will be 11.51 of OpenStax. What's coming up? OpenStax 11.51. Okay, so this says a twin-sized air mattress. Used for camping. Has dimensions of 100 centimeters by 200. I'm sorry, yeah, by 200 centimeters by 15 centimeters. When blown up. The weight of the mattress is 2 kilograms. Okay. How heavy a person? Could the air mattress hold? If it is placed in fresh water? Okay, so a twin-size air mattress used for camping has dimensions of 100 centimeters by 200 centimeters by 15 centimeters when blown up. The weight of the mattress is 2 kilograms. How heavy a person could the air mattress hold if it is placed in fresh water? So effectively, we're putting the air mattress in water. We're going to figure out how heavy a person can be in there such that the mattress and the person don't sink. All right, so let's see. How do we do this? I'm going to erase this. All right, so first of all, let's figure out the volume of the air mattress. So the volume will be what? We want to put it in, so we want to put it in terms of meters. So 100 centimeters is 1 meter. 1 meter times 1 meter, or times 2 meters. Times 0.15 meters. So the volume of the air mattress, in this particular case, will be 0.30 meters cubed. Okay, now the maximum weight you're trying to figure out the maximum weight the mattress can support. Maximum weight that the mattress can support is the weight that just submerges the air mattress. All right, so that's what we're talking about. So basically, we want the weight of the mattress to be such that it would equal the volume of the water submerged. We want to just be at that pivotal point of submersion. All right, so we would say that the volume of the water that would be submerged would equal the volume of the mattress, or 0.30 meters cubed, right? So when I get to the point where we're literally just having, the fraction submerged will be just at 1.0. All right, so the argument so far. Now we can employ Archimedes' principle. All right, so Archimedes' principle states that the buoyant force is the weight of the fluid submerged, or in this case, the weight of the water. The fluid is the water. So the buoyant force would be the weight of the water submerged. We know what the volume of that is. So how would you figure out the weight of the water submerged? Well, the buoyant force would be what? It's mass times gravity, right? What's mass? Rho water. The volume that we just got done calculating times G. Okay? So the buoyant force will be it's fresh water, so it's 1,000 kilograms per meter cubed. The volume that we calculated just a few seconds ago was 0.30 meters cubed. And acceleration of gravity, 9.80 meters per second squared. So the buoyant force, that would be pushing, of the water pushing up on the air mattress will be 2,940 newtons. Okay, so we'd have to have, that's the buoyant force. So we're literally talking about a balance of forces. Okay, we got the buoyant force now, so remember that. We need a balance of forces now. So essentially, for this special situation, the weight of the air mattress plus the person okay, that must balance the buoyant force. So it must just equal the buoyant force. In mathematics, that means that the mass of the mattress plus, I'll let the person have a mass of m is the mass of the person, times g has got to equal F buoyant. That's the condition. All right, so what we're going to do now is figure out what the weight of the person is, right? And so again, I can distribute gravity. I have the mass of the mattress times g. M times g is this weight of the person that I'm looking for. All right, and that's equal to F buoyant. All right, so I want to look for the weight of the person. So the weight of the person is F buoyant minus the mass of the mattress times g. Okay, and I could go one more line here. So that means the weight of the person is equal to, well, I figured out the buoyant force earlier, it's 2940 newtons, minus the mass of the mattress. Well, we were told that was 2 kilograms, times 9.80 meters per second squared. All right, and so when I do this calculation, I'll just erase this little top part here. When I do that calculation, I find out that the maximum weight that a person could be for the mattress not to sink, the maximum weight would be 2,920 newtons. That's the maximum weight of the person on the air mattress in the water, such that the person plus the air mattress do not sink. All right. That's it for fluid statics. Now, again, that's fluid. Those are fluids and stationary fluids. Now we discuss fluids in motion. And that's called fluid dynamics. All right. And so fluid dynamics, we have to kind of introduce a few new concepts. So we just got done with fluid statics. Now we will discuss fluid dynamics. That's fluids in motion. So fluid dynamics now. Okay, that's fluids in motion. And so one of the things to talk about is, let's imagine for a moment I have a pipe. And in this pipe is fluid flowing. Let's imagine here that I'm going to take a chunk of this fluid for consideration. So I'm going to consider a chunk of the fluid. Okay, I'm going to imagine the area, cross-sectional area is A. We're going to imagine the length of this chunk of fluid is going to be D. All right, and the idea is, well, we want to calculate what's called a flow rate. Okay, the flow rate Q, we use capital Q, cap Q for it, is defined. To be the volume of fluid passing by some location through an area during a period of time. Okay. So the flow rate Q, capital Q, is defined to be the volume of fluid passing by some location. Let me consider some location here. Through an area, there's your area, during a period of time. So get this volume that's going to pass through this area per unit time. So we would say that so by definition, the flow rate, capital Q, would be that volume divided over a period of time, T. What volume would that be? Well, that volume would be the constant area times the distance divided by time. Or I can take, or I can, you know, when I have a product, I can divide by either A or D. So I'll just write it as A D over T. Well, this distance per unit time, we would think of this as an average fluid velocity. It's as if this volume is moving along the fluid at a certain velocity. It's the distance, the total distance that this fluid travels in a period of time. We assume that this entire volume of fluid will pass through this little location, this line of demarcation, during a time t. So the area is constant. D divided by T, we think of that as an average fluid velocity. So I can actually call this, I can say that little d over T, we can think of it as a average velocity. So I can define V bar, V over bar, as D over T, and that is an average velocity of the fluid flow. And then what I can say is this D over T, I can then write the flow rate, Q, cap Q, as the area times the average velocity. Or a little b. The area, cross-sectional area times the average velocity. So a couple of different ways I can write the flow rate. Again, capital Q. So what should the flow rate be? Well, the flow rate, its units are meters cubed. So the units on the flow rate is meters cubed per second, generally. Meters cubed per second. It's a volume per unit time. A volume passing some plane. If I imagine cutting the pipe through by a plane, plane, it would be the volume of that fluid per unit time. Now, what happens if I do the following? What happens instead if I imagine a different kind of a pipe? So let's say now I have a pipe that has bigger cross-sectional area. Then all of a sudden, it crimps down. Into one that has a much more narrow cross-sectional area. Okay. And so what I can do is I say, well, let's consider a chunk of fluid out in a bigger area. We can say that the area in the bigger region will say is A1, and the fluid is flowing at average velocity, we'll say V1. And then we take a chunk of fluid in the nozzle here. We say that that area is A2, and it's flowing at some V2. Now, we employ, here's the difference between, so we generally discuss fluids altogether, right? We generally lump gases or liquids and gases together as fluids. But there is one major distinction. Between liquids and gases. So gases are compressible. Very compressible. You can compress gases very easily. Liquids are generally incompressible. That's very important. Liquids are generally incompressible. Means you can apply pressure on them all over, but they're not going to deform to a smaller volume. They're incompressible. We want to employ the concept of, generally speaking, in fluid dynamics, we generally employ the concept that fluid is incompressible. All right. So, and if you go to engineering school, you actually will take an entire one semester course on fluid mechanics, right? And so when you talk about fluids of motion in general, we make the assumption of an incompressible fluid. In fluid dynamics. Essentially, this means that the flow rate is constant. The fluid is not bunching up, if you will. Anywhere. You know, for instance, like in blood flow, you want incompressible fluid in blood flow. If you have blood flow bunching up in places, as I say, you're going to have coagulation. You'll have clots. You don't want that. You want the fluid to just keep on flowing. All right. And so we want to make the assumption here is we want to make an assumption of compressible flow. I'm sorry, incompressible flow. We'll have to make the assumption of incompressible flow. What that means then is we have a constant flow rate. All right, so incompressible flow means constant flow rate. Okay, so Q1, whatever the flow rate is, let's say I'll call this 1, is going to equal Q2. Cap Q1 equals cap Q2. The flow rate is constant no matter where I cut it. That means that A1 V1 equals A2 V2. Cross-sectional area A1 times the velocity of the fluid at V1 equals cross-sectional area A2 times the velocity V2. We call this the continuity equation in fluid mechanics. Okay, very important equation. This is a continuity equation where you make the assumption of incompressible flow, which means constant volume flow rate. Constant volume flow rate. That means that A1 V1 is A2 V2. Again, constant volume flow rate. Okay, that's a continuity equation. One of the big time governing equations in fluid mechanics. Extremely important equation. Oh, I cannot write the letter T. All right, constant volume flow rate. We'll do a couple of problems. I'll do now, as I said, in OpenStax, chapter 11 was fluid statics, chapter 12 was fluid dynamics, right? So you're going to see the chapter number, you're going to see the numbers going to 12 now. That's because there was a brief chapter on fluid dynamics in OpenStax. So OpenStax 12.1. All right. That says is what is the average flow rate? Flow rate. In centimeters cubed per second. Okay. Of gasoline of a car traveling at 100 kilometers per hour. If it averages 10.0 kilometers per liter. All right, so we're driving cars like we would in Canada or Mexico. You know, we're not in the United States. We do kilometers per hour and kilometers per liter. Okay. All right, so how do you do this problem? Okay, so basically what this tells me is it takes 1 liter of gasoline to travel 10 kilometers. That's what that little ratio tells me. So it takes 1 liter of gasoline to travel 10 kilometers. Okay. And so if one travels 100 kilometers per hour, all right, then one uses what? 100 kilometers per hour there's 1 liter per 10 kilometers, like I said up here. And so what we're getting is 10 liters of gasoline per hour. Okay. Now, what would that be in centimeters cubed per second? Now I have liters per hour. Now I got to convert that to centimeters cubed per second. All right. So that's my flow rate, but those are not the right units. I mean, that's my answer, but those are not the right units. All right. So the next part of this problem is just to convert. All right, 10 liters per hour. All right, so I have 10 liters per hour. Okay, and then what? Well, let's see, a decimeter cubed per liter. And 1 liter is 1 decimeter cubed. All right, so liters are gone. All right, I have decimeter cubed. Now I know there are 0.1 meters in a decimeter. And of course, it's a volume, so I have to cube this. Now my decimeters are gone. Now I have meters cubed per hour. And of course, there are 100 centimeters in a meter. Got to cube that. That gets rid of these meters cubed. And what else? Well, I have an hour has 3,600 seconds. So 60 times 60. Hours are gone. I do all that calculation, I will get my flow rate in centimeters cubed per second. So when I do all this calculation, I find out that my answer should be 2.78 centimeters cubed per second. Okay. All right. I'm going to go to OpenStax 12.13. All right. That says water is moving at a velocity of 2.00 meters per second. Through a hose. With an internal diameter of 1.60 centimeters. Right. 1.60 centimeters. Okay, A. What is the flow rate in liters per second? All right, and B. The fluid velocity in the hose's nozzle is 15.0 meters per second. Okay, what is the nozzle inside diameter? Okay, 12.13. Water is moving at a velocity of 2.00 meters per second through a hose with an internal diameter of 1.60 centimeters. A, what is the flow rate in liters per second? And B, the fluid velocity in the hose's nozzle is 15.0 meters per second. What is the nozzle inside diameter? Okay, so what are we talking about? Let's draw a picture. So what we have is very similar to the original picture I drew before. We have, we have a portion that's the main hose. All right, so this hose is going to have water flowing through it. I'm taking this section. And eventually what's going to happen is it will crimp down to the nozzle. Okay, now we would say that the area of the hose is A1, and there's going to be a velocity of water there. We'll call it V1. And then when we go to the nozzle, this part here is the main hose. Fill the nozzle, the area will be a smaller area, cross-sectional area A2, and the velocity coming out will be B2. All right, so it's kind of like, if you're if you have just a basic hose and you have water flowing through, and you basically pinch it with your fingers, you crimp it down. You're essentially have created a nozzle. You notice that the water will shoot out a lot faster. It's basically the same principle. Because water is incompressible, it essentially, if you reduce the area, you got to keep the flow rate the same, so you increase the velocity, keep the flow rate the same. All right, so we use the continuity equation. right, so for A, now, the first part is we just want to find the flow rate, right? And so we would say that A1 V1 is A2 V2. All right, and again, we remind ourselves that V1 we were told was 2.00 meters per second. All right, we're told the diameter D1, inside diameter of the hose, 1.6 centimeters or 0.016 meters. We're told V2 was going to go all the way up to 15.0 meters per second. We don't know anything at all about D2. We're eventually going to want to find that. But really, the first thing we really want to do is figure out, it wants to find the flow rate. All right, so we want to find the flow rate. So we can find the flow rate through the product. Either of these products are supposed to be the same. Turns out we know everything about the left-hand side. So before we do anything else, why don't we just use the information on the left-hand side to find the flow rate? All right, so part A, that's what it wants, is just the flow rate. So I know everything on the left-hand side. Let's just compute the flow rate, you know, and then we can go and do part B. So the flow rate, I can pick either side. I mean, I happen to know about everything at 1. So flow rate is going to be A1 V1, or we want it in liters per second. So we're going to write it as, what's A? Well, it's pi D1 squared over 4. That's the area at 1, and then we have V1. So that'll give us pi D1, as we remembered, was 0.016 meters squared divided by 4, and V1 was 2.0 meters per second. Okay, and so we would find that if you do this, we have Q is equal to 4.021 times 10 to the negative 4. It's a flow rate, meters cubed per second. But we don't want it in those units. We want it liters per second. So I got to do a couple of conversions. So what do we know? Well, we know that basically 1 decimeter is worth 0.1 meters. Don't forget to cube it. That gets rid of meters. And now I have decimeters cubed, and of course I know that a liter is equivalent to 1 decimeter cubed. So a liter is 1 decimeter cubed. So my flow rate becomes 0.402. Liters cubed, or sorry, liters per second. All right, 0.402 liters per second. Right, that's part A. Part A says I want the flow rate. Okay. Now we'll do part B. All right, so part B, I'm actually going to now utilize the continuity equation. What I want is I want to figure out what the nozzle diameter is. All right, so now I'm going to employ the continuity equation in its full glory. And I'll say, okay, well, continuity equation. Well, it's going to be A1 V1 is A2 V2, or maybe I'll just write the. I'm looking for information about at location 2, so I'll write A2 V2 is A1 V1, or I'll write that A2 is pi d2 squared over 4. V2 is pi d1 squared over 4 v1. I get rid of the pi's and the 4's. All right, so I can write that basically d2 squared v2 is d1 squared v1. All right, and I can solve. I'll just write it over here, I guess. So d2 squared v2 is d1 squared v1, and I'm looking for d2. So I can write this as d2 squared is v1 over v2 d1 squared. Take the square root of both sides. I find that d2 is the square root of v1 over v2, and that's all multiplied by d1. All right, and so I'm just going to do one last thing here. So d2, oops. So d2 will be the square root of what so v1 is 2.0 meters per second. V2 is 15.0 meters per second. Take the square root. That becomes a unitless number. And then D1, we found out that D1, it was 0.016 meters. So D2 will be 0.58, or, well, actually, I would call it, let's be, because I have a unitless number there. I can just go back to calling this 1.6 centimeters. Let's squeeze this in here. All right, which means that D2 becomes 0.584 centimeters. Oops. Okay, so you have to really crimp it down to get 15 meters per second flow rate. I'm sorry, to get 15 meters per second velocity, and of course you'll maintain the flow rate doing that. All right, one last topic of fluid mechanics, and that is called the famous Bernoulli equation. So the Bernoullis were actually a very successful family of mathematicians and physicists, excellent level physicists. The Bernoulli equation, again, the Bernoulli family, Bernoulli, the one that is responsible for this equation is Daniel Bernoulli. He had, I think his father was, maybe his brother was Jacob Bernoulli, and his father was, drawing a blank here, but the Bernoulli family is a very, very highly successful family of mathematicians. So this was Jacob Bernoulli who is responsible for this particular derivation. So we're going to derive what's called a Bernoulli equation. So I'm going to actually look at a funny looking pipe. So I'm going to imagine I have a pipe. Wire down here. And then the pipe is going to come up. Okay, so we're going to imagine that there's going to be some fluid That's gonna, let's go imagine like a volume of fluid in the lower part, the lower, wider part of this pipe. Okay, so this is going to be given by, there's an area, we'll say A1. And let's say the fluid has a velocity V1 at the lower part of the pipe. Higher up, we have another chunk we can consider. We'll say the area here is A2, and it has a velocity V2. Okay. Now, we're going to imagine that there is a zero potential energy to down here, like a floor. And the average height of the fluid in the lower, wider part, we'll call that H1. And at the higher level, we'll say the higher level, right around the median here, or the medium of it, is H2. Above, what we refer to down here is the zero of potential energy. Well, we'll say particularly the zero of gravitational potential energy. So kind of keep this in mind. Now, one of the first things you want to say is, well, there's going to be a displacement. So we can imagine there being some sort of a P1, a pressure 1 located over here, and a pressure P2 located on the top. So there'd be some sort of a force F1 imagined on the one side, and the other side we'd have a force F2. All right, and so if we imagine, first of all, that there's going to be some sort of work that's going to be associated with this problem. You know, the fluid flow, this section of fluid, let's say, we'll imagine that whatever the force F1, because there's a pressure P1 there, it's actually going to cause a displacement of X1. On the other hand, there's going to be a force F2 that's going to cause a displacement of X2 on the other side. So we imagine that the change in the work will be F1x1 minus F2x2. Okay, there'll be a difference in the work. F1x1, F1 and F2 are opposed to one another. F1x1, F2x2. The fluid, chunk of fluid that we're considering in this lower area, 1, is going to displace by amount x1. And the chunk of fluid in the upper area at 2, because of F2, will displace by an amount x2. Okay? And that would be a change in the work. Now, we don't talk about forces, we talk about pressures, right? So we know the pressure P1 is going to be F1 over A1, and the pressure P2 is F2 over A2. All right, so again, we dress up the forces in terms of pressures and areas in fluid mechanics. So we can take this upper equation for the work, and instead we can write it as delta work is P1 A1 X1 minus P2 A2 X2. Dressing it up in terms, instead of the forces, we now can replace those in terms of pressure times energy. Pressure times area. All right, and And then what we know is we can say, well, we can essentially say that A1x1 is A2x2, which equals a volume V. They're the same volume V because, let's remind ourselves of 0% energy. The same volume V because the fluid is incompressible. We have incompressible fluid. So what this then means is I can take this equation. Delta work is going to be, especially it's going to be P1V minus P2V, or the change in the work as computed is going to be the quantity. I can pull out that common volume V, and it's going to be P1 minus P2 times the volume. That's the change in the work. We imagine this fluid flow that the change in the work will be imagining F1 moving the fluid in by a displacement x1, and F2 moving the fluid in by a displacement x2. We dress up the forces in terms of pressures and areas. We rewrite the change in work in terms of pressures and areas. We invoke the concept that the fluid is incompressible. So A1x1 and A2x2 are both the same incompressible volume, which means that I can then say that the change in work is P1 volume minus P2 volume, or delta work is P1 minus P2, that quantity times this consistent volume. Okay, that's an important piece of information to take with us. Okay, so I'm going to put that on in the on my little parking lot. I'll stick that up here. So important piece of information is this equation right here. I'm going to erase all the other stuff in my derivation. Okay, and then so the important piece of information what I've derived so far is the change in the work in this fluid flow. All right, is equal to P1 minus P2 times the volume. Okay, we'll put that in the parking lot. Now, with this fluid flow, we also need to invoke that there has to be a, we need to employ the work energy theorem. So we have to figure out what the change in the energy is, the total mechanical energy. So the change in total mechanical energy, we can think of this as, again, we want to look at the change in total mechanical energy. Now, in past problems, you know, like say for instance, when I was looking at the conservation of energy for systems like with collisions, like let's say pool balls colliding or billiard balls colliding, well, I was always able to say that the potential energies were the same, and because the pool table was the same height, so I end up really having to only consider kinetic energies. Well, in this case, clearly there is a difference in gravitational potential energy between 1 and 2. So when I do the conservation of mechanical energy, I have to include both the potential energy and the gravitational potential energy and the kinetic energy. All right. So if I talk about the change in total mechanical energy, okay, That's going to be the mechanical energy at 2 minus the mechanical energy at 1. I have to consider both of them. All right, so let's consider that. I want to keep my picture up here, so I need to minimize real estate. So again, change in mechanical energy is the energy at 2 minus the energy at 1. But what's that going to be? Well, that's going to be the potential energy at 2 plus the kinetic energy at 2 minus the quantity, the potential energy at 1 plus the kinetic energy at 1. Okay? And so what we're going to say now is say, well, the total mechanical energy. Well, what's the potential energy at 2? Well, it's going to be mgh2. And the kinetic energy, well, 1/2 mv2 squared. Minus the potential energy at 1, mgh1 plus 1/2 mv1 squared. All right, and so what we then say is we can then say, well, we're going to employ now a work energy theorem. All right, so we're going to employ the work energy theorem. So work energy theorem implies what does that mean? That means that the change in the work is equal to the change in the total mechanical energy. In this case, you know, we compare everything. What's that mean? Well, that means that I can combine what I see up here. Okay, I'm going to actually erase my picture now. I think we got the gist of it. All right, and so let's erase the picture, and let's in lieu of the mathematics. So we know a picture that we're working toward. All right, and so we got the work energy theorem. So the work energy theorem says okay, that says that the change in the work is the change in the total mechanical energy. What's the change in the work? I computed that before. That's going to be P1 minus P2, the pressures at both places times the volume. That's the work. That's equal to all of this stuff. So that's going to be mgh2 plus 1/2 mv2 squared minus mgh1 plus 1/2 mv1 squared. And that's what I have. That's all of this stuff down here from the total change in mechanical energy. All right, now, of course, I don't want to discuss masses in terms of, I don't want to discuss mass directly. I need to discuss it in terms of density times volume, right? So remind ourselves that the mass, when we think of it as the density of the fluid times the volume, and of course the volume element is always the same because of incompressibility. So I can rewrite all this as P1 minus P2 on the left side. I'm not going to change the left side at all for a while. But the right side, what do we have? Well, we're going to have, instead of mass, I'm going to have rho B G H2 plus 1/2 rho B little v2 squared minus rho B G H1 plus 1/2 rho v v1 squared. Okay, all I've done is I've taken the mass and turned into the density times the volume. Now, one of the things I can do is I can cancel the volume throughout. The volume is the same everywhere because of incompressibility. So everywhere you see volume, you can now cancel it out at this point. All right, so what do I know? I have P1 minus P2 is equal to, I have rho g H2 plus 1/2 rho V2 squared minus rho g H1 minus, I gotta plug the minus sign through everything, 1/2 rho V1 squared. Okay, and now I can rearrange. And so I have P1. I'll put all the ones together, right? So P1 plus 1/2 rho V1 squared plus rho g H1, okay, equals P2 plus 1/2 rho V2 squared plus rho g H2. Okay, so P1 plus 1/2 rho V1 squared plus rho g H1 equals P2 plus 1/2 rho V2 squared equals rho plus rho g H2. Well, what does that mean? That means that if I compute, the pressure, and again, this is a pressure equation. Every term in this is a pressure. So if I take it at any given point, the pressure plus 1/2 density times the velocity, the speed 1 squared, speed of the fluid at 1 squared plus rho g H1 from the potential energy, and I take it, and it's going to equal pressure at 2 plus 1/2 rho V2 squared plus rho g H2. What that basically says is, anytime I compute these quantities, they are always adding up to the same thing. So this is a conservation of energy type of situation, but if I want to be very general about it, what I'm basically saying is that, and again, this is the Bernoulli pressure equation. Everything in here is a pressure. I can say that when at any point in the fluid, P plus 1/2 rho V1 squared plus rho g P plus 1/2 rho V squared plus rho g H equals a constant. This special equation is called a Bernoulli equation. Now your book just gives it to you, but the reality is the Bernoulli equation is derived via the conservation of energy applied to a fluid. So we're kind of walking through, I guess, all of the mechanics again with fluids. Now we're in the energies. So essentially, at any given point in the fluid, each one of these, this is the pressure that I just got. This is the static pressure, if you will. This is a pressure caused by this is from the kinetic energy term. It's caused by the flow of air or flow of a fluid, I guess, if you will. And this is the potential energy term. And when you calculate this is always a constant. Now, this is how airplanes fly. So if I imagine for a moment, for the Bernoulli equation, let's say I apply it to an airplane. So let's say I have an airplane wing. I have an airplane wing. I have to have it specially shaped. So what's going to happen here is the airplane wing, you can imagine, the airplane is flying, let's say, this direction. And so this airplane wing is shaped. It's, here's where it touches the fuselage, and here's the end of it. And what's going to happen is the wing shape makes the air on top of the wing accelerate. Because as air flows over the wing, there's going to be air on top that's going to accelerate, and faster than the air on the bottom. This is faster air, and this is slower air. Okay, and in simple terms. Well, how would I apply Bernoulli's equation? Well, I essentially would say, well, let's look at, so I'm going to erase my little wing here, and I'm talking the top and the bottom, right? So I'm going to apply the Bernoulli equation. I'm going to say, well, let's look at, compare the top and the bottom here. So we'll say P top of the wing, plus 1/2 rho V top squared, and top of the wing. And I'll say, I'll call the vertical axis Z. So I'll say rho G Z top. And that's equal to P bottom plus 1/2 rho V bottom squared plus rho G Z bottom. I'm applying Bernoulli's equation on the top of the wing, just on the top of the wing, and just on the bottom of the wing, right? Now we make the assumption that, Z top, the wing is thin, so the wing is relatively thin. So Z top is about equal to Z bottom. So potential energy terms cancel. Okay, make the thin wing assumption. All right, so that means I can get rid of these two potential energy terms. All right, and so in that case, I can get rid of this term and the bottom term here. So I can say that essentially that P top plus 1/2 rho V top squared is P bottom plus 1/2 rho V bottom squared. All right, now these two terms have to add up to be a constant. So that means that if V top is greater than V bottom, the air flowing over the top of the wing accelerates because of the wing shape. Then that means that if V top is greater than V bottom, that means that P bottom, to make up for it, P bottom must be greater than P top. All right. So, if you multiply by the areas, the area of the wing that means that F bottom is greater than F top. And we have a lift force. And we have flight. So effectively, going back to your wing, if here's your wing again, I mean, if this is F bottom, and this is F top, F bottom being greater than F top means you have an overall net lift force. That is what makes an airplane fly. The Bernoulli equation is why airplanes fly. So every time you get on an airplane, it is being lifted up by its wings. It is being flown because of Bernoulli's equation. F bottom over minus F top, that's your overall lift force. F bottom is greater than F top. That means the airplane experiences a lift. It flies. Okay, let's do, I'm going to close out. I'm going to do basically one problem here on Bernoulli, and then we'll call it a done deal. All right, so here we go. I'm going to do OpenStax 12.21. All right, that problem says every few years, winds in Boulder, Colorado attain sustained speeds of 45.0 meters per second. Or about 100 miles per hour. When a jet stream Colorado's pretty high up, descends during early spring. Okay, approximately what is the force? Due to the Bernoulli effect, on a roof. Having an area of 220 meters squared. It makes a side comment. It says typical air density in Boulder is 1.14 kilograms per meter cubed. And corresponding atmospheric pressure is 8.89 10 to the 4th newtons per meter squared. All right, so boulder's high up. So typical air density in Boulder is 1.14 kilograms per meters cubed. And corresponding atmospheric pressure is 8.89 10 to the 4th. Pascals. All right, and then it makes a comment here. Bernoulli principle, as stated in the text, assumes laminar flow. Okay, it's generally a laminar type principle. Using the principle here, it produces only an approximate result because there is significant turbulence, of course. All right, so that's what they say. So again, we're not going to worry about that. We're going to simplify things. So again, every few years, winds in Boulder, Colorado attain sustained speeds of 45.0 meters per second, about 100 miles per hour, when the jet stream descends during early spring. Approximately what is the force due to the Bernoulli effect on a roof having an area of 220 meters squared? Typical air density in Boulder is 1.14 kilograms per meters cubed, and the corresponding atmospheric pressure is 8.89 times 10 to the 4th pascals. All right, so this is one of those things where you wonder, like in a case of a tornadic type of a storm, with a tornado, the high wind is parallel to the ground. Yet you wonder, why do roofs get lifted off houses? Well, it's because of the Bernoulli effect. So essentially, what I'm going to consider here is I'm going to make a little house, real simple here, and on the outside, so on the outside are going to be high winds, and they're going to be basically more or less parallel to the house. So right out here are very high winds, and I can refer to this as V, and my outside pressure would be P out. That's the pressure outside of this house. Inside the house, I'll have pressure P in, and certainly I don't expect to have any kind of wind in the house. So in the house, the wind would be zero, stagnant air in the house, so just stationary air. And this is inside the house. Okay, high winds outside. Now I'm gonna apply Bernoulli's equation. So I would say that Pn, or sorry, let's see here, P out plus, let's write it even further to the left here. All right, P out plus 1/2 rho V out squared. Again, rho is the density of air. That's the fluid we're talking about now. Plus rho G Z out. That's the height above, let's say, zero potential energy. Just on above my roof. That's going to equal Pn plus 1/2 rho V in squared plus rho G Cn. Now I'm going to make a similar case, like I said, with the airplane wing. I'm going to say that, well, Cn. So I don't expect there to be much difference in height. So just outside my roof and just inside my roof is about the same. So we'll say that Cn is about equal to C out. And so potential energy terms cancel. Also, I don't expect wind inside my house, so Vn is 0. Right, so we can take and simplify this Bernoulli equation really quickly. All right, so with that said, I can actually cancel out rho g Zn with rho g Z out. And my rho g Vn squared, well, Vn is 0, so I can cancel that out too. The only thing on the other side is just Pn. When I make those assumptions, my Bernoulli equation simplifies to this. Then I can basically say, I can subtract the p's and say, well, now I have a delta p. Okay, I'm subtracting, I have one p minus the other one, is 1/2 rho v out squared. That's the change in the pressure between inside and outside, just inside my roof and just outside my roof. And now what? Well, now I'm going to multiply both sides by A, the area of the roof. So delta P times A, area of the roof, is then going to be 1/2 rho A V out squared. That is the lifting force. That's the force that's going to lift the roof off of my house. 1/2 rho A V out squared. Okay? So let's write the equation up here and solve for it. So we have, again, the force that will lift the roof off of my house is 1/2 rho A V out squared. Plug in our values now. That lift force is 1/2. The density of air in Boulder, Colorado, as we just got done being told, is 1.14 kilograms per meter cubed. That's the density of air in Boulder. And the area of the roof is 220 meters squared. Again, I was given that in the given as well. That's the roof. And we're told 45.0 meters per second, and we need to make sure we square the virtually. So when you do all of this, you find out that the force that the wind that's really going parallel to the roof, the force is going to cause it to lift the roof off your house because of Bernoulli effect will be 2.54 times 10 to the 5th newtons. That is a very big force. So this is why when you see tornadic storms, you see tornadoes or very, very, very high straight line winds, you see roofs being lifted off of houses, because that is the principle involved here. It is the same principle that causes airplanes to fly. It is the Bernoulli effect. It is an application of the Bernoulli equation. All right. And with that, that's my video for chapter 11.